Hello there, and welcome to the Drift to Stars. I'm so glad you found your way here tonight. Whatever kind of day it was, long or quiet, heavy or scattered, you made it here. And that's enough. This is a place with no rush, no urgency, nothing you need to remember in the morning. Just a voice and some of the most beautiful, unanswered questions the universe has ever quietly kept to itself. And just before we begin, if these calm, curious explorations help you unwind, consider liking and subscribing to the channel. It helps others find their way here too, one sleepy soul at a time. Now, if you're ready, let's begin. There is a question so large that science cannot find the edges of it. Not the question of how stars are born, or why oceans are blue, or what lies at the center of a black hole. Those are enormous questions, and we will visit them tonight. But beneath all of them, there is one that sits older and quieter than the rest. Why is there something rather than nothing? Imagine not darkness, not cold space, not an empty room, but the complete absence of existence itself. No space to be empty, no time to pass, no laws to be broken, just nothing, in every direction, in every dimension, forever. And then somehow, from that absolute nothing, everything. Science can trace the universe back nearly 14 billion years. It can describe the first fractions of a second after the beginning, the temperatures, the forces, the first particles flickering into being. But it cannot reach the moment before, because there may not have been a moment before. It cannot say why the laws of physics exist. It cannot explain why anything is here at all. Quantum physics tells us that even a perfect vacuum is not truly empty. Particles blink in and out of existence constantly, like tiny whispers of reality appearing and vanishing before they can be heard. Some physicists wonder whether the universe itself arose the same way that absolute nothingness is somehow unstable, that existence is simply what emptiness becomes when left alone long enough. Others imagine an endless sea of universes, each one flowering into being with its own rules, its own constants, its own stars. But even that only moves the question one step back. Why should anything exist to generate them? There is no telescope that can answer this. No particle accelerator, no equation. Every atom in your body, every photon of light that has ever touched your eyes, all of it rests on a foundation that cannot be explained. The fact that you are here, breathing slowly in the dark, is the deepest mystery science has ever faced. And the universe, for all its vastness, offers no explanation, only the quiet fact of its own existence. That existence had a beginning. Scientists call it the Big Bang, though the name is a little misleading. There was no explosion into space, because space itself did not yet exist. There was, instead, a sudden appearance of everything: space, time, energy, heat beyond imagining, and then expansion in all directions simultaneously, from a point smaller than any word could hold. We can trace that story back with remarkable precision. We know the temperature of the universe when it was 1 second old. We know the ratio of hydrogen to helium forged in the first 3 minutes. We can still hear the echo of that early fireball, a faint hum of microwave radiation that fills the sky in every direction, left over from a time when the universe was a glowing sea of light. But there is a wall we cannot see beyond. A moment, not even a moment, an unimaginably small fraction of a second, before which our equations collapse, before which our understanding simply stops. What triggered it? Why then? And not before, or after, or never? Some theories suggest the Big Bang may not have been a beginning at all, but a transition, a universe before ours collapsing and bouncing into a new expansion. Others propose it arose as a quantum fluctuation, the way particles appear from nothing in a vacuum, only on the scale of an entire cosmos. But all of these ideas rest on other questions they cannot answer, and asking what came before the Big Bang may not even be meaningful if time itself was born in that instant. Then before has no definition. It is like asking what is south of the South Pole. The spark that set the cosmos in motion is still hidden, and the silence where an answer should be is, in its own way, extraordinary. Time began then, or perhaps time became something measurable, something that could carry events in sequence, one after another, in the direction we call forward. You feel it right now. The moment you are in will never come again. The one before is gone. The one ahead hasn't arrived yet. This feels so obvious that it barely seems worth naming, and yet it is one of the strangest unsolved problems in all of physics. The laws that govern the universe, the equations that describe how particles move, how forces interact, how light travels, are almost entirely symmetrical in time. Run them forward, run them backward. The mathematics does not care. A particle interacting with another particle follows the same rules in either direction. Nothing in the fundamental equations demands that time should only move one way. And yet, a broken glass never leaps from the floor back into your hand. Heat flows from your warm coffee into the cooler air, and never the other way. You remember yesterday and not tomorrow. The universe, at every scale you can perceive, insists on moving in one direction only. Scientists connect this to entropy, the tendency of systems to move from order toward disorder. A universe that begins in an extraordinarily organized state will naturally grow more disordered over time. And we do seem to live in a universe that began with remarkable order and has been slowly unwinding ever since. But that only shifts the question. Why did the universe begin in such a low entropy, highly ordered state that time could have a direction at all? No one knows. You experience time every second of your life. You feel it flowing, carrying you gently from one moment to the next. And still, the reason it flows forward, only forward, always forward, remains one of the most quietly haunting mysteries in science. Some of that universe is visible to us. The stars, the galaxies, the faint glow of nebulae, all of it together, every atom of every planet, every beam of light, every particle of gas in every cloud between the stars, adds up to less than 5% of what the universe actually contains. 5%. The rest is something else entirely. When astronomers measure the way galaxies spin, they find that the stars at the outer edges move far too fast. By the laws of gravity, as we understand them, those stars should drift away into open space. There is simply not enough visible matter to hold them, and yet they stay. Something is holding them, something invisible, something that does not glow, does not absorb light, does not emit any signal we have yet learned to hear. We call it dark matter, and it is everywhere. It wraps around galaxies like an invisible cocoon. It bends the paths of light from distant objects, curving them the way a lens curves glass, not because we can see the dark matter, but because we can see what it does to the light passing by. It forms a vast web stretching across the entire universe, a skeleton of invisible scaffolding on which all visible structure is built. Experiments buried deep underground, shielded from the noise of the surface, cooled to temperatures near absolute zero, wait in absolute stillness for a dark matter particle to pass through. They have been waiting for decades. So far, the silence continues. Whatever dark matter is, it is not made of the same stuff as you. It passes through walls, through planets, perhaps through you right now, without leaving a trace. 5 times more abundant than everything you have ever seen or touched, and completely unknown. And yet dark matter, for all its mystery, is not even the largest unknown, because the universe is not just sitting still, held together by gravity, slowly aging in place. It is expanding. Every galaxy is moving away from every other galaxy, carried by the stretching of space itself. This much was known since the 1920s. What no one expected was what astronomers discovered in 1998. The expansion is speeding up. Galaxies are not just drifting apart. They are accelerating away from each other, faster with every passing moment, as if something embedded in space itself is pushing them. Something with no mass, no charge, no detectable presence, only an effect, quiet and relentless, working across every cubic centimeter of empty space in the universe. We call it dark energy, and it makes up nearly 70% of everything. We do not know what it is. One possibility is that it is a property of the vacuum, that empty space carries a kind of energy, a built-in pressure pushing outward. Another is that it is a field slowly changing over time, like a tide rising across the whole of creation. Some physicists wonder if it means our understanding of gravity itself is incomplete. What is certain is this: the fate of everything depends on it. If dark energy remains constant, the universe will expand forever, cooling and thinning until only silence remains. If it strengthens, it could eventually tear apart not just galaxies and stars, but atoms themselves. And still, right now, in this very moment, it pushes silently, invisibly, across every inch of the universe, and we do not know what it is. This universe, the one made possible by dark matter and dark energy, and the particular laws that govern them, seems, in a very specific and strange way, to have been arranged for life. Not designed, not necessarily, but arranged, as if by some extraordinary coincidence. The strength of gravity, the charge of an electron, the mass of a proton, the force that binds atomic nuclei together. These numbers are what they are, and they are precise. Change any of them by even a fraction, by 1 part in a million. In some cases, and stars would never ignite, or atoms would never form, or the universe would collapse before anything interesting could happen. Physicists call this the fine-tuning problem, and it is genuinely unsettling in a quiet way, not because it proves anything, but because it raises a question no equation can answer. Why these numbers? There are a few ways to sit with the question. Perhaps there are countless universes, each with different constants, a vast landscape of possibilities, and we simply find ourselves in one of the rare ones where the settings allow for atoms and chemistry, and eventually, eyes that can look up at the sky. Perhaps there is some deeper principle, still undiscovered, that fixes the constants in place the way physical laws fix the shape of a snowflake. Perhaps it is a coincidence so large it looks like intention, without being one. Or perhaps the answer is something no one has yet imagined. What we know is this: the universe you are resting in right now is, by any measure we have, improbably suited for your existence. And why that is so remains one of science's most quietly beautiful open questions. Beyond you, beyond this room, beyond the atmosphere, beyond the planets and the nearest stars, the observable universe stretches for about 46 billion light-years in every direction. Everything within that sphere is, In principle, something we could study, something that has had time to send us a signal. But there is an edge. Not a wall, not a barrier, just a horizon. A distance beyond which light has not had time to reach us in the nearly 14 billion years since the universe began. Beyond that horizon, reality continues. But what it contains, we may never know. Perhaps it is much the same. More galaxies, more stars, more planets, the same laws playing out across different circumstances. Perhaps it is radically different. Some theories of inflation, the extraordinary rapid expansion thought to have occurred in the universe's first moment, suggest that our observable patch is just one small region in a vastly larger whole. That what we can see is, in the truest sense, only a beginning. Whether the universe beyond our horizon is finite or infinite, whether it curves back on itself like the surface of a sphere, or stretches outward without end, remains genuinely unknown. The cosmic microwave background, that ancient afterglow of the early universe, carries faint patterns that might someday tell us the shape of everything. So far, it only tells us that the universe is very nearly flat, and that beyond what we can see, the mystery continues. And perhaps it continues in more ways than one, because some of the most serious physicists working today believe, though they cannot prove, that our universe is not the only one. The idea of the multiverse arises naturally in certain theories. Cosmic inflation, if it happened the way many models suggest, would not have stopped everywhere at once. Different regions of space may have stopped inflating at different times, each one becoming its own bubble, its own universe with its own constants, its own laws, its own particular arrangement of forces. Our universe would be one bubble among an uncountable many. String theory adds another layer, predicting a vast landscape of possible realities, each corresponding to a different configuration of the theory's fundamental ingredients. In this picture, the fine-tuning problem dissolves. Of course, our universe has the right constants for life. Only in universes with the right constants can anyone ask the question. But here is where the mystery deepens rather than resolves. If other universes exist beyond our cosmic horizon, no light or signal could ever cross the distance between us. No experiment we could ever run would confirm their existence. An idea that cannot be tested sits at the edge of science and philosophy, both genuinely possible, genuinely fascinating, and for now, genuinely beyond our reach. The possibility that reality is larger than our universe, perhaps infinitely larger, is one of the most extraordinary ideas human minds have ever held, and it remains beautifully unproven. If there are other universes, they may be built on different versions of the fabric that holds ours together, because this universe runs on a fabric, a strange, dynamic, invisible stage on which everything takes place. Einstein called it space-time, and he showed that it is not fixed and passive, but alive in its own way. It bends around mass. It stretches as the universe expands. It ripples when enormous objects collide, sending waves that take 1 billion years to reach us but can still be felt, faintly, in the most sensitive instruments ever built. But what is space-time made of? What is the stuff that bends? At the largest scales, Einstein's equations describe it beautifully. But at the smallest scales, inside atoms, among particles, a completely different set of rules takes over. Quantum mechanics describes a world that is grainy, uncertain, probabilistic, and quantum mechanics and general relativity do not agree. When physicists try to apply both at once, the equations break down, producing infinities where there should be answers. Some researchers believe space-time is not fundamental at all. that it emerges from something deeper, perhaps from the quantum entanglement between particles, woven together into a geometry we experience as space and time. In this picture, what feels like the stage is actually a surface, and beneath it lies a reality we have not yet found the language to describe. Others go further, wondering if time itself, the flow you feel so constantly and so intimately, might be an illusion, a pattern in something deeper that has no time in it at all. The stage on which the universe performs its long, slow story may be stranger than anything that performs upon it. And on that stage, at scales far smaller than anything you could ever touch or see, something stranger still is happening. Something that has been confirmed by experiment after experiment, that forms the foundation of modern technology, and that no one, not one physicist in the century since it was discovered, has been able to fully explain. A particle can be in two places at once, not approximately, not in a loose, poetic sense. A single electron, a single photon, a single atom can exist in a superposition of states, occupying multiple positions simultaneously, until the moment something interacts with it, and it settles into one. Picture a coin spinning in the air. While it spins, it is neither heads nor tails, it holds both possibilities at once. That is a rough image, but the quantum reality is stranger even than that. Because the electron is not secretly one thing while appearing to be two, it genuinely, physically exists across multiple possibilities at the same time. Its wave function, the mathematical description of everything it might be, spreads through space like a ripple on still water. And this is not theory. Scientists have created superpositions not just with electrons but with molecules thousands of atoms large, with clusters of particles you could almost imagine holding. The quantum world bleeds upward into scales that once seemed safely classical. Does the particle physically inhabit two places? Or is the superposition only a reflection of our incomplete knowledge, a description of what we don't yet know, rather than what truly is? No interpretation has been proven. No one has settled the question. The particle holds its secret in both hands, offering neither, and the universe says nothing to explain it. That silence deepens when two particles meet in a particular way. Because sometimes, two particles do not merely interact and separate. They become entangled, their properties linked in a way that distance cannot touch. Measure one, and you instantly know something about the other. Not approximately, not with some delay proportional to how far apart they are. Instantly, regardless of whether they are on opposite sides of a laboratory or opposite sides of a galaxy. Einstein called it spooky action at a distance, and he did not mean it kindly. He believed it revealed a flaw in quantum theory, that there must be hidden information, hidden variables, passing between particles in ways we hadn't detected. He believed the universe did not work this way. He was wrong. Experiments across decades, growing more precise with every iteration, have confirmed that entanglement is real, that no hidden message passes between the particles, that the correlation is not a coincidence or a trick of incomplete knowledge, but a genuine feature of reality. Two particles, separated by any distance, remain in some sense one system, not connected by a thread we can see, but by something deeper than connection. What that means, no one can fully say. Some physicists believe it points to a non-local universe, one in which space is not the fundamental separator it appears to be. Others think it suggests that information, not matter, is the true foundation of reality. Still others hold that entanglement may be the thread from which space-time itself is woven. We use it. Quantum computers rely on it. Quantum encryption is secured by it. And still, In the same breath, we admit we do not understand it. The universe whispers between its particles across any distance, and we are only beginning to learn the language. What makes the quantum world stranger still is not just what particles do when no one is looking. It is what happens the moment someone does. In the famous double-slit experiment, particles are fired one at a time toward a barrier with two narrow openings. When no one measures which slit each particle passes through, something extraordinary appears on the screen behind an interference pattern, the signature of a wave passing through both openings simultaneously. The particle, alone, interferes with itself, but when a detector is placed at the slits, when the experiment is arranged so that it is possible, in principle, to know which path the particle took, the interference pattern vanishes completely. The particle behaves like a particle again, passing through one slit or the other, leaving two simple bands on the screen. The act of observation changes the outcome. Not because the detector physically disturbs the particle. Physicists have been careful about this, endlessly careful, designing experiments to rule it out. The mere fact that information about the particle's path exists somewhere, in any form, is enough to collapse its wave-like behavior. Why should reality care whether it is being watched? What counts as an observation? A detector? A human eye? A conscious mind? Or simply any interaction that leaves a lasting record anywhere in the universe? These questions have no agreed answer. Physicists have argued about them for a century. Some say every possibility branches into its own universe at the moment of measurement. Others say the wave function never truly collapses, only appears to, from our limited perspective. Others still believe consciousness plays a role that physics has not yet accounted for. The line between observer and observed is not where common sense placed it, and the universe, it seems, draws that line somewhere we have not yet found. Step back from the small, and the strangeness does not disappear. It only changes shape, because at the scale of everyday experience, at the scale of planets and people and the force that holds you gently against the earth right now, there is a mystery hiding in plain sight. Gravity is extraordinarily weak. This seems wrong. Gravity feels powerful. It pulls the oceans into tides, holds the moon in orbit, keeps the atmosphere wrapped around the planet. It shapes the paths of stars and bends the fabric of space-time itself. And yet, compared to the other forces of nature, gravity is almost absurdly feeble. A small magnet can lift a paperclip clean off the table, overcoming the gravitational pull of an entire planet with a force generated by a piece of metal you could hold between two fingers. The electromagnetic force is roughly 10,000 billion times stronger than gravity. The strong nuclear force, which holds atomic nuclei together, is stronger still. Why the gap? Why should one of the four fundamental forces be so dramatically weaker than the others? Some physicists think gravity may leak into hidden dimensions, extra dimensions of space curled up at scales too small to detect, into which gravity spreads and dilutes, while the other forces remain confined. Others believe the true strength of gravity is comparable to the others, but masked by unknown physics at tiny distances. Still others suspect the answer lies in a deeper theory that unifies all four forces into one. Whatever the answer, the weakness of gravity is not incidental. It is the reason stars burn slowly enough to last billions of years. The reason galaxies can form without collapsing instantly. The reason there is time for life to arise at all. The mystery built into gravity's quietness is, in a strange way, the mystery of why you exist. And the deepest expression of that mystery is this: the two greatest theories in the history of science cannot be made to agree with each other. General relativity, Einstein's description of gravity, space, and time, has been tested to extraordinary precision. It predicts the orbit of Mercury to within a fraction of an arcsecond. It predicted the bending of starlight around the Sun, confirmed during a solar eclipse in 1919. It predicted gravitational waves, ripples in space-time itself, which were finally detected a century later by instruments sensitive enough to measure a change in length 1/10,000th the diameter of a proton. Quantum mechanics has been tested with equal precision. Its predictions for the behavior of electrons match experimental results to more than 10 decimal places, the most precisely confirmed theory in the history of human knowledge. Both are right. Both pass every test. And they cannot both be right at the same time, in the same place, because when you try to combine them, when you try to describe a situation where gravity and quantum effects both matter, like the interior of a black hole or the first instant of the universe, the mathematics produces answers that are not merely wrong, but meaningless. Infinities where finite answers should be. Divisions by zero where real physics should live. Somewhere beneath both theories, there must be a deeper truth, a theory of everything, patient and unified, waiting to be found. String theory reached for it. Loop quantum gravity reached for it differently. Neither has been confirmed. Neither has made a prediction that experiments have yet been able to verify. The two pillars of modern physics hold the universe up between them, and they do not touch. Where they both fail most dramatically is at the center of a black hole, because a black hole is the place where gravity wins completely, where mass collapses inward past every threshold, past the point where light can escape, past the point where any signal can carry information outward, down toward the center. And at that center, according to Einstein's equations, everything converges to a point of infinite density, a singularity. Infinite density means infinite curvature of space-time. Infinite curvature means the equations no longer function. The mathematics does not merely become difficult, it becomes undefined. Whatever is happening at the center of a black hole, our best theory of gravity cannot describe it. This is almost certainly not because infinite density is what is actually there. It is almost certainly because general relativity is reaching the edge of its validity, the place where a deeper theory must take over, where quantum gravity, whatever it turns out to be, must reshape the singularity into something finite and real. But we do not have that theory yet. And even if we did, we could not test it. The event horizon, the invisible boundary around a black hole, beyond which nothing can return, seals whatever is inside, away from every observation we could ever make. The heart of a black hole is not merely far away. It is permanently beyond reach, a region of the universe that will never answer our questions, because no answer could ever make the journey out. Singularities appear not only inside black holes, but at the very beginning of the universe. That first moment, before time had settled into its current rhythm, before space had expanded to a scale where familiar physics applied. In both places, the equations point to infinities. In both places, they are telling us something important. They are telling us they have been pushed past where they were designed to go. Most physicists believe singularities are not real features of nature, but symptoms of incompleteness, places where a better theory would smooth the infinity into something finite and describable. The singularity at a black hole's center might become a tiny, dense, stable core. The singularity at the universe's beginning might dissolve into a quantum fog of space-time, from which the Big Bang emerged as a kind of phase transition. But we do not know, and there is something quietly profound in sitting with that. Every map has an edge, Every theory has a boundary where it stops working, and something else must begin. The singularity is that edge, drawn in the sharpest terms physics knows how to use. It is not a failure of science, but an honest acknowledgement that the story continues past what we have yet learned to read. Beyond the singularity, the universe keeps its most private chapters, and it has not yet let us turn the page. There is another chapter. A black hole keeps hidden, one that troubles physicists not because of what happens to matter falling in, but because of what happens to information. In physics, information is not just data. It is the complete description of a physical system, every position, every momentum, every quantum state of every particle. And one of the deepest principles of quantum mechanics holds that information is never truly destroyed. It may be scrambled beyond recognition, spread across countless particles in impossibly complex patterns, but it is never gone. Somewhere, in some form, it persists. Now consider a black hole. Matter falls in stars, gas, perhaps a spaceship, perhaps a library, carrying within its atoms all the information of everything it ever was. The black hole swallows it. And if, as Stephen Hawking showed in the 1970s, the black hole eventually evaporates, slowly radiating energy over unimaginable timescales, until nothing remains, where does that information go? If it is destroyed, quantum mechanics is violated. If it escapes, encoded somehow in the radiation leaking out, then something extraordinary must be happening at the event horizon. Some mechanism, invisible to our current theories, imprinting everything that ever fell in onto the particles that slowly leak back out. Some physicists think information is stored holographically on the surface of the event horizon itself. Others think black holes connect to other regions of spacetime, allowing information to escape through channels we cannot see. Others believe quantum mechanics itself must be revised. A century from now, someone may look back at the black hole information paradox the way we look back at the ultraviolet catastrophe that preceded quantum mechanics as the crack in the foundation through which an entirely new physics entered the world. While that question waits for its answer, black holes continue doing something even more extraordinary, something Hawking predicted, but that no one has ever directly observed. They glow, not brightly, not in any way a telescope has yet been able to detect against the noise of their surroundings. But according to the mathematics that emerges when quantum theory is applied near an event horizon, pairs of particles are constantly flickering into existence, just outside the black hole's edge, one particle falling in, one escaping outward. Over time, this process slowly drains the black hole of mass. Given long enough, far longer than the current age of the universe, for any black hole of stellar mass or larger, the black hole would eventually evaporate completely. This is Hawking radiation. It is one of the most celebrated predictions in modern theoretical physics, a rare place where quantum mechanics and general relativity meet and manage, however tentatively, to speak the same language. And it has never been seen. The signal would be too faint, too cold, overwhelmed by the cosmic background and the turbulent environments surrounding real black holes. Laboratory experiments have created analogs using sound waves in flowing fluids to mimic the conditions near an event horizon and found hints. But hints are not confirmation. If Hawking radiation is real, it changes everything about how we understand black holes. If, somehow, it is not if some subtlety of the true theory of quantum gravity alters the picture, then something even stranger must be happening in the space, just beyond the point of no return. Either way, the universe has more to say. And perhaps the most extraordinary thing it might say is this, that what we call a black hole, this region of no return, this seal on the universe's most private information, might not be an ending at all. Einstein's equations, when solved in certain ways, produce a remarkable result. They suggest that the geometry of space-time inside a black hole might connect through a tunnel, a bridge, a fold in the fabric, to another region of space-time entirely. These structures are called wormholes, and whether they can exist, whether they could be stable, whether anything could pass through them, remains genuinely open. Most physicists believe that even if wormholes can form, they would collapse almost instantly, their throats pinching shut before anything could travel through. Keeping one open would require a form of matter with properties that may not exist, but the mathematics does not forbid them outright. Some researchers have explored the idea that the singularity at a black hole's center might mark not an ending, but a seam, a place where one region of space-time gives way to another, perhaps seeding the birth of a new universe, carrying within it the information and the physics of its parent. In this picture, black holes are not graves, but nurseries, and our own universe may have been born inside one. These ideas are speculative, beautifully, hauntingly speculative. No observation has confirmed them, but the universe has surprised us before, and the mathematics, patient and indifferent, leaves the door open. Even as you rest right now, black holes are turning quietly in the dark, holding their secrets, perhaps holding much more than secrets, and the equations that describe them still have things left to say. Long before any black hole had aged enough to carry such mysteries, the universe was dark. Not dark the way a room is dark when the lights go out, a familiar darkness, comfortable, full of the memory of light. This was a different kind of dark, a darkness with no memory of light at all, because light as we know it had not yet been born in any star. For hundreds of millions of years after the Big Bang, the universe expanded in silence. Hydrogen and helium drifted in vast, slow clouds, cooling as space stretched around them. No fire, no warmth, no photon of visible light traveling between one place and another, just gas and gravity and patience. And then, slowly, the clouds began to fall into themselves. We call what followed the cosmic dawn, the moment the first stars ignited and flooded the universe with light for the first time. It is one of the most dramatic transitions in the history of everything, and we have never seen it happen. The first stars, astronomers call them population 3 stars, would have been unlike anything that exists today, born from pure hydrogen and helium, with none of the heavier elements that seed later stars with complexity. They may have been hundreds of times more massive than our sun. They would have burned with savage brightness, living only a few million years before dying in catastrophic explosions that scattered the first heavy elements, carbon, oxygen, iron, into the space around them. Those elements became the next generation of stars, and the next. And eventually, in the heart of a later star, the atoms that now make up your body were forged. The James Webb Space Telescope is peering further back in time than any instrument before it, searching for the faint light of those first fires. It has found galaxies earlier than expected, stars forming sooner than our models predicted. But a true population 3 star, pristine, enormous, burning on nothing but the original ingredients of the universe, has not yet been confirmed. Somewhere in the early dark, the first fire caught. We are still looking for where. While those first stars burned and died, something else was growing in the darkness between them. Something that should not have been possible, given the time available. At the center of nearly every large galaxy, including our own, sits a black hole of staggering mass. Not the stellar mass black holes left behind when ordinary stars collapse, those are heavy, but manageable. These are supermassive, millions of times the mass of the Sun. Billions, in the most extreme cases. We understand roughly how they grow. Gas falls in. Stars are disrupted and swallowed. Smaller black holes merge. Over long timescales, mass accumulates, and the black hole at the center of a galaxy grows with it. But the timescales matter enormously, and when astronomers look deep into the early universe, looking back in time, because light takes time to travel, they find black holes that are already billions of times the mass of the Sun, when the universe is less than 1 billion years old. There simply was not enough time, not by any mechanism we currently understand. A black hole growing by swallowing gas, even voraciously, cannot accumulate that much mass that quickly. Something else must have happened. Perhaps the first black holes formed not from collapsing stars but from the direct collapse of enormous primordial gas clouds, skipping intermediate steps entirely. Perhaps they grew through mechanisms that don't operate the same way today. Perhaps our understanding of how matter falls into black holes in those extreme early conditions is simply incomplete. These ancient giants sit at the centers of the earliest galaxies we can observe, patient and enormous, daring us to explain them. And so far, we cannot. Around those early black holes, the first galaxies were taking shape. Gravity gathered gas into structures. Stars clustered into groups. Groups merged into larger assemblies. And in time, something beautiful began to emerge across the universe. A shape that appears again and again, across billions of light years, in hundreds of billions of galaxies. The spiral, 2 arms, sometimes more, curving outward from a bright central region, sweeping through space like the surface of a slow whirlpool. Our own galaxy is one. Andromeda, our nearest large neighbor, is another. Spiral galaxies are not rare curiosities. They are among the most common large structures in the observable universe, and we do not fully understand why. One idea is that the arms are not solid structures at all, but density waves regions where stars and gas pile up as they orbit, the way cars bunch together in a traffic slowdown on a highway, without the slowdown itself moving with the traffic. The arms, in this picture, are patterns, not permanent groupings. Stars pass through them, brighten briefly as new star formation is triggered by the compression, and continue on their way. But simulations of galaxies don't always reproduce the elegant, stable spirals we observe. Interactions between galaxies can generate spiral structure, and so can the influence of a central bar of stars rotating through the nucleus. The roles of dark matter, of magnetic fields, of stellar feedback from supernovae, all of these play into the shape. When you imagine the Milky Way from above that soft pinwheel of light, 200 billion stars arranged in patient, curving arms, you are imagining something whose full explanation has not yet been written. From within that spiral, signals reach us from far across the universe. Most of them carry information. We can slowly decode the spectrum of a star, the redshift of a galaxy, the temperature of a gas cloud. But occasionally, something arrives that carries no clear return address. A flash, a burst of radio waves lasting no more than a few milliseconds, releasing, in that vanishing instant, as much energy as the sun produces in an entire year. Fast radio bursts. Hundreds have now been detected, arriving from all directions, from distances of billions of light years. Some appear once and never again. Others repeat, sometimes in patterns, sometimes seemingly at random. They pass through intergalactic space, and the gas between galaxies slows different frequencies by different amounts, allowing astronomers to measure, with remarkable precision, how much matter the signal passed through on its journey. In this way, fast radio bursts have become unexpected tools for mapping the invisible gas that fills the spaces between galaxies. But what produces them remains genuinely uncertain. Magnetars, neutron stars with extraordinary magnetic fields, have been linked to at least some fast radio bursts. One was detected from within our own galaxy, tracing back to a known magnetar, and that burst alone was 1,000,000 times more powerful than any pulsar emission ever seen. But not all fast radio bursts fit the magnetar picture. Some may come from merging neutron stars, some from processes in the early universe, some from mechanisms not yet proposed. Every few days, somewhere in the universe, something screams in radio waves and falls silent. We hear it, we measure it carefully, and we still do not know who is speaking. Closer to home within our own galaxy, scattered among familiar stars, there are objects whose silence is, in its own way, just as mysterious as those screaming bursts, because pulsars do not scream. They tick. A pulsar is what remains after a massive star exhausts its fuel and its core collapses. A neutron star, city-sized, crushed to a density where a teaspoon of its material would weigh 1,000,000,000 tons. It spins, and as it spins, beams of radiation sweep through space like the beam of a lighthouse, hitting Earth once per rotation with extraordinary regularity. When pulsars were first discovered in 1967, the signal was so regular, so precise, so unlike anything natural astronomers had previously encountered, that the researchers briefly labeled it LGM-1, Little Green Men. They were not little green men, but the precision remains astonishing. Some pulsars rotate hundreds of times per second, and their timing drifts by less than a microsecond over years of observation. They keep time better than atomic clocks, better than almost anything humans have ever built. How does an object so extreme maintain such regularity? The density, the strong magnetic field, the superfluid interior, these play roles. But the detailed physics of what happens inside a neutron star, at pressures and temperatures beyond any laboratory on Earth, is still not fully understood. And sometimes, a pulsar glitches its rotation, suddenly speeding up in a fraction of a second, then slowly relaxing back. Something shifts deep inside, in regions where the physics is unlike anything else in the known universe. What exactly shifts and why remains an open question, ticking quietly in the dark. Near some of those pulsars, and scattered elsewhere through the galaxy, there are objects even more extreme. Objects that make ordinary neutron stars seem gentle by comparison. A magnetar is a neutron star with a magnetic field 1,000,000,000,000 times stronger than Earth's. Strong enough that if one existed at the distance of the moon, it would erase every credit card on the planet and pull the iron from your blood. Strong enough that the field itself contributes significantly to the object's energy budget, distorting its crust, building stress in its surface layers the way pressure builds in rock before an earthquake. And then, sometimes, that stress releases. In a fraction of a second, a magnetar can release more energy than the sun produces in 100,000 years. Gamma rays and X-rays flood outward in a pulse so intense that a burst from a magnetar 50,000 light-years away, on the far side of our galaxy, visibly disturbed Earth's upper atmosphere when it arrived in 2004. From 50,000 light-years away, what triggers these eruptions is not fully understood. The leading ideas involve starquake sudden shifts in the rigid crust of the neutron star as the magnetic field twists and the surface adjusts, or sudden reconfigurations of the magnetic field itself, snapping into a lower energy state and releasing the difference as radiation. But magnetars are rare, difficult to observe, and surrounded by environments so energetic that their details are hard to read. They sit at the edge of what matter can be compressed, magnetized, spinning, erupting, and what happens inside them belongs to a physics we are still learning to speak. Further out, beyond the magnetars and the pulsars and the gas clouds of our galaxy, particles arrive from the deep universe, carrying energies that should not exist. Cosmic rays, mostly protons. Some heavier nuclei rain down on Earth constantly. Most come from familiar places. The sun produces them during solar flares. Supernovae accelerate them to high energies as their shock waves expand through surrounding gas. These we understand, at least in outline. But some cosmic rays arrive with energies so extreme that no known process should be able to produce them. A single particle, a single proton, carrying the kinetic energy of a baseball thrown by a professional pitcher, not a beam of particles. One particle, one proton, accelerated to within a fraction of a percent of the speed of light, carrying macroscopic energy in a single quantum of matter. Physicists call the most extreme of these oh my god particles. The first was detected in 1991 over Utah. Its energy was so far beyond what theory predicted could survive the journey across intergalactic space that researchers initially questioned whether something had gone wrong with the instruments. Nothing had gone wrong. Where do they come from? The leading suspects are active galactic nuclei supermassive black holes, actively consuming matter, generating jets of energy that could perhaps accelerate particles to these extremes. But magnetic fields in intergalactic space bend the paths of charged particles, erasing the directional information that would point us back to the source. Somewhere in the universe, nature runs a particle accelerator of incomprehensible power. We feel its output, one particle at a time, arriving from a direction we cannot trust, from a place we cannot name. Between the sources of those particles and the galaxies and the filaments of the cosmic web, there are places where almost nothing exists. Not low density, almost nothing. Voids stretching for hundreds of millions of light years in every direction, containing so few galaxies that looking into them is like looking into the most complete emptiness the universe has managed to produce. Gravity should prevent this, to some extent. Even small overdensities in the early universe should attract matter, pulling it into filaments and clusters. The spaces left behind should be empty. Yes, but not this empty. The largest known void, sometimes called the cold spot void, associated with an anomalously cool region in the cosmic microwave background, stretches for nearly 1 billion light-years. Its existence is difficult to explain without invoking something beyond the standard picture. Perhaps a subtle influence of dark energy, shaping large-scale structure in ways our models haven't fully captured. Perhaps a statistical anomaly, rare but possible in an infinite universe. Perhaps something not yet in our theories. Voids are not merely absences. They leave imprints on the light that passes through them, shifting the temperature of the cosmic microwave background in ways that can be mapped and measured. They are, in their emptiness, as informative as the structures they surround. But why they are as large as they are, and whether the largest of them are telling us something new about the physics of the cosmos, remains an open question. The universe, it turns out, is as mysterious in its empty places as in its full ones. All of this, the voids, the filaments, the galaxies, the black holes at their centers, the stars and their planets, exists within a universe that began and will, in some form, end. And how it will end depends almost entirely on the one thing we understand least: dark energy. If dark energy is what it currently appears to be, a constant energy density of empty space, steady and unchanging, then the universe will expand forever. Galaxies will drift apart until they vanish beyond each other's horizons, invisible across distances grown too large for light to bridge. Stars will exhaust their fuel one by one. The last red dwarf will cool over timescales so long that the number of years would take more digits than there are atoms in the observable universe to write. And then only cold, dark remnants will drift through an expanding void, growing ever more isolated, ever more silent. This is the heat death, not a dramatic ending, but a slow, permanent fading. The universe spending itself entirely and going dark. But if dark energy changes over time, growing stronger, tightening its grip on the fabric of space, then something more dramatic may await. Structures that gravity currently holds together would begin to lose that contest. First galaxy clusters, then individual galaxies, then solar systems, then planets, then the chemical bonds holding molecules together, then the nuclear forces holding atoms themselves, all overcome, eventually, by a dark energy that grows without limit until it tears the very fabric of space-time apart. The Big Rip. Every structure in the universe, down to the subatomic, unraveled in a final moment of total dissolution. Which fate is coming, or whether the truth is something neither model has imagined, we cannot yet say. The data we have is consistent with a constant dark energy, but the uncertainty in our measurements is wide enough to allow the alternatives. The universe has not yet told us how its story ends. What we do know is that it began with extraordinary speed. In the first fraction of a second, not the first second, not the first millisecond, but an interval so small that writing it as a decimal would require dozens of zeros before reaching any meaningful digit. The universe is thought to have undergone a period of expansion, so rapid it makes everything that came after seem leisurely. Inflation. The universe doubling in size, again and again, in less time than light takes to cross a single proton. Space itself, stretching faster than light, could travel through it, not violating the speed limit, because the limit applies to things moving through space, not to the expansion of space itself. This idea explains several puzzles simultaneously. Why does the universe look the same in every direction, even though regions on opposite sides of the sky were never, under normal expansion, close enough to have interacted? Inflation brought them together before stretching them apart. Why is the universe so geometrically flat when it could have been curved in either direction? Inflation ironed out the curvature, the way stretching a small piece of a balloon makes it appear flat. And the tiny quantum fluctuations frozen into the universe during inflation, microscopic ripples, stretched to cosmic scales, seeded the variations in density that eventually became galaxies and clusters and everything. But what caused inflation? What was the field, the inflaton, physicists call it, that drove this extraordinary expansion? And why did it eventually stop? These questions have answers in theory but not in observation. The fingerprints of inflation are visible in the pattern of the cosmic microwave background, but the mechanism behind them is still debated. Something made the universe grow unimaginably fast in its first moment, and then it stopped. And in the quiet after that stopping, everything we have ever known began. In the quiet after that stopping, on a small rocky planet orbiting an ordinary star in one arm of an ordinary spiral galaxy, something happened that may be the most extraordinary event in the history of the universe. Chemistry became alive, not in a flash, not in a single moment that could be pinpointed and studied. Gradually, over timescales that dwarf every human civilization ever built, the molecules present on the young Earth, simple things, carbon and hydrogen and oxygen and nitrogen, arranged in small configurations, began to do something remarkable. They began to copy themselves. We know life was here early. Fossil evidence of microbial life pushes back more than 3.5 billion years, to a time when Earth was still being pummeled by asteroids, still cooling from its violent formation, still finding its way toward the relative stability that followed. By all indications, life appeared almost as soon as conditions allowed it, which suggests either that life arises readily whenever the ingredients are right, that it is, in some sense, what chemistry does when given enough time and energy, or that we are extraordinarily lucky, and the speed of life's appearance on Earth is a coincidence that says nothing about how likely it is elsewhere. We do not know which. The origin of life is not one mystery, but many layered inside each other. How did the first self-replicating molecule form? How did it acquire a membrane to separate itself from the chaos outside? How did the genetic code, the precise, near-universal language in which life writes its instructions, come to be? Each question has hypotheses, some of them compelling, none of them confirmed. What we know is that somewhere, in conditions we are still trying to reconstruct, the threshold was crossed. And on the other side of it, the world was permanently different. Where that threshold was crossed is its own question, and the candidates are as different from each other as it is possible to imagine. Picture the deep ocean floor not as it is today, but as it was 4 billion years ago. In certain places, where tectonic activity forces hot water up through the seafloor, there are vents. Not the superheated black smokers that first come to mind, but gentler systems, alkaline hydrothermal vents. Their chimneys built from minerals, precipitated out of warm, chemistry-rich water. These structures contain tiny chambers, pores in the rock, naturally separated from the surrounding ocean. Some researchers believe these pores were the first cells, not biological cells, but mineral compartments that concentrated molecules, maintained chemical gradients, and provided the sheltered conditions in which the first self-sustaining chemistry could organize itself. In this picture, life did not build its first container. It borrowed one, already waiting in the rock. Others look upward, toward the surface, toward shallow pools on early land left behind by tides, by rain, by the ebb and flow of water across volcanic terrain. These pools would have concentrated and dried, driving chemical reactions that might not occur in a dilute ocean. Ultraviolet light from the young sun, harsher then, without an ozone layer to filter it, might have powered key steps in building RNA and other complex molecules. Both environments are plausible. Both have experimental support. Both face serious objections. And the rock record from 4 billion years ago has been so thoroughly transformed by time and geology that the direct evidence, if it ever existed in readable form, may be gone. The cradle of life is somewhere on this planet. We simply don't know where. Whatever the setting, the most astonishing transition was not the first molecule or the first chemistry. It was the first boundary. A cell is not merely a collection of useful molecules. It is a collection of useful molecules that knows it is separate from everything outside it. That boundary, the membrane, is what makes the difference between a chemical reaction and a living thing. Without it, there is no inside, no protection, no concentration of the right ingredients in one place, no possibility of maintaining the delicate conditions life requires. How did the first membrane form? Certain molecules, called fatty acids, have a remarkable property. One end is attracted to water, the other repels it. When such molecules are placed in water, they spontaneously arrange themselves into spheres, their water-hating tails tucked inward, their water-loving heads facing out, forming a bubble that can enclose a small pocket of solution. This happens in laboratories today, with molecules that would have been present on the early Earth. The bubbles form readily. They can absorb additional fatty acids from their surroundings, growing larger. They can divide when they reach a certain size. They can, in some conditions, take in RNA from outside and hold it inside. These are not cells, but they are extraordinary. They are the shadow of cells, structures that arise from simple chemistry and already exhibit in primitive form several of the behaviors we associate with life. The gap between these simple bubbles and even the simplest known living cell is still enormous. The molecular machinery inside a modern cell, the ribosomes, the enzymes, the precisely coordinated systems of protein synthesis and energy production, is staggeringly complex, and how it arose from something so simple remains one of biology's deepest open questions. The first cell was the beginning of everything that came after, and how it assembled itself from the materials of a young, chaotic planet is still, at its heart, unknown. Inside every cell that has lived on Earth for the last several billion years, the same molecule carries the instructions, the same structure, the same pairing rules, the same elegant double helix, read in the same direction by the same molecular machinery. DNA. Its universality is one of the most striking facts in biology. The genetic code, the correspondence between sequences of nucleotide bases and the amino acids they specify, is nearly identical across every living thing on the planet, from the bacteria in soil, to the cells of your body, to the sequoias, and the blue whales, and the tardigrades drifting through a film of water on a rooftop somewhere. This universality tells us something important. All life on Earth shares a common ancestor. Every living thing is cousin to every other living thing, separated by varying lengths of time, but connected by an unbroken chain of descent, stretching back billions of years to something we call Luca, the last universal common ancestor. But it raises a question: why this molecule? And why this shape? RNA is simpler than DNA, and most researchers believe RNA came first capable of both storing information and catalyzing chemical reactions, a single molecule that might have bootstrapped the first living systems. DNA, more stable and more protected, may have taken over as a more reliable archive once life had grown complex enough to maintain it. But the precise shape of the double helix, the specific pairing of bases, the specific geometry of the spiral may not have been inevitable. Other nucleic acids can be synthesized in laboratories, some of them capable of carrying information and evolving. Whether DNA's specific structure was the only viable solution, or one of many that happened to win, is unknown. Every strand of DNA in every cell of your body right now carries a 4 billion-year-old question, written in a language that only one kind of life has ever used. Why this language and not another is still being asked. Before DNA, and perhaps alongside the first RNA, other entities were already learning to persist in the world, not by replicating their own genetic material exactly, but by something stranger, by borrowing the machinery of others. Virus. They are not alive in the way a bacterium is alive. They do not metabolize, do not generate their own energy, cannot reproduce, without entering a living cell and commandeering its ribosomes and enzymes to make copies of themselves. By most definitions, they sit at the edge of life rather than within it, and yet they are ancient, extraordinarily diverse, and woven deeply into the history of every living thing on Earth. About 8% of the human genome consists of sequences derived from ancient viral infections, remnants of viruses that integrated themselves into the DNA of our ancestors and were passed down through generations, some of them eventually co-opted by their hosts for new purposes. Where did viruses come from? 3 hypotheses compete without resolution. Perhaps they are relics of the RNA world, pre-cellular replicators that survived into the era of cells by learning to depend on them. Perhaps they began as fragments of cellular genetic material that escaped and acquired the ability to reinfect. Perhaps they were once free-living organisms that became progressively reduced, losing everything not essential to the one thing they do. The truth may be all 3 viruses may not have a single origin, having arisen in different ways at different times, a family defined not by ancestry but by lifestyle. They blur the line between the living and the chemical. They have shaped the evolution of every complex organism on Earth, and where they came from, precisely, remains one of biology's most enduring open questions, hovering at the edge of the question of what life itself means. Life crossed a threshold once, as far as we know, but the materials for that crossing were not uniquely terrestrial. They were everywhere. Amino acids, the building blocks of proteins, have been found in meteorites. Nucleobases, the molecules that form the rungs of the DNA and RNA ladder, have been detected in interstellar space, drifting in molecular clouds between the stars. Complex organic molecules form in the cold, radiation-bathed environment of space through chemistry that requires no biology at all. The early Earth was bombarded heavily by asteroids and comets during a period called the Late Heavy Bombardment, roughly 4 billion years ago. These impactors would have delivered enormous quantities of organic material, ready-made ingredients for the chemistry of life, arriving from across the solar system, and perhaps from further still. So the question of why some molecules became alive while others did not is not only a question about Earth, it is a question about chemistry itself. Given the right ingredients, and those ingredients seem to be common, is the emergence of self-replicating, evolving chemistry inevitable? Or is there a further step, some specific arrangement or environment or event that is vanishingly rare? If life is inevitable wherever conditions allow, then the universe is almost certainly full of it on planets we have not yet visited, in oceans beneath ice we have not yet drilled, perhaps in forms we would not immediately recognize. If life requires something more, something rare or accidental, then the silence that surrounds us might be the silence of genuine solitude. The answer matters more than almost any other answer science could find, and it is still completely unknown. Because even if life arose easily on Earth, the question of whether it has arisen anywhere else remains entirely open. We have searched carefully and persistently. Radio telescopes have swept the sky for decades, listening for signals that might carry the signature of intelligence, mathematical patterns, narrowband emissions, anything that would stand out against the natural noise of the cosmos. The sky remains quiet. We have analyzed the atmospheres of exoplanets, worlds orbiting other stars, looking for gases that biology produces and physics alone does not easily explain. The results are intriguing in places, ambiguous everywhere, and conclusive nowhere. We have sent probes to Mars, which once had liquid water and perhaps the conditions for life. We have found complex chemistry in its soil, evidence of an ancient wet world, hints of possible methane fluctuations in its thin atmosphere. We have found nothing that clearly requires biology to explain. We have detected thousands of exoplanets, many of them rocky, many of them in the habitable zones of their stars, many of them with conditions that might support liquid water on their surfaces. The galaxy appears to be full of worlds, full of chances, and from all of them, so far, silence. This does not mean we are alone. The distances are immense. Our searches so far have covered a vanishingly small portion of the possibilities, and life, even intelligent life, might communicate or exist in ways we have not thought to look for. The silence is not an answer. It is only an absence of an answer, but it is a silence that, on quiet nights, can feel very large. And perhaps the silence persists, partly because we do not know, even in principle, what we are looking for, because all our definitions of life come from a single example. Every living thing we have ever studied is built from the same handful of elements, uses the same basic chemistry, relies on liquid water as its solvent, stores information in nucleic acids, and builds its machinery from proteins. This is an extraordinary convergence, but it may reflect the history of life on Earth, rather than the requirements of life in the universe. Could life exist built around silicon instead of carbon? Silicon sits just below carbon in the periodic table and can form long chains. In theory, silicon-based polymers could carry information, but silicon chemistry is less flexible than carbon chemistry. Silicon bonds with oxygen to form solids rather than gases, and the range of reactions available to silicon under ordinary conditions is narrower. It might work, but not easily, and probably not in a world with liquid water. What about ammonia as a solvent instead of water? Ammonia remains liquid at temperatures far below water's freezing point, opening the possibility of life on worlds too cold for liquid oceans. What about life in liquid methane, on a world like Titan, where hydrocarbon seas exist at temperatures that would freeze most Earth chemistry solid? These are not idle questions. They determine what we look for when we search. If life can only arise in conditions like Earth's, our search has clear targets. If life can arise in conditions we have not imagined, then it might already be present somewhere we have dismissed as lifeless, and we would not know to look. And what we find, even on Earth, suggests that life is far more resilient than it once appeared. The conditions we once thought necessary for life, moderate temperatures, liquid water, access to sunlight, turn out to be sufficient, but perhaps not required. Extremophiles, organisms that thrive in conditions once considered lethal, have expanded the boundaries of the possible, with every new environment explored. Bacteria living in the cores of nuclear reactors, metabolizing radiation, organisms in the hyperacidic drainage of copper mines, in the crushing pressures of ocean trenches, in the bone-dry soils of Antarctica, where almost no moisture exists. Tardigrades, which can survive the vacuum of space, extreme radiation, complete desiccation, and temperatures approaching absolute zero. How common are truly habitable worlds, given this expanded definition of habitable? The answer changes depending on how flexible life can be. If life requires something close to Earth's conditions, then habitable worlds may be rare, perhaps one in millions of planets across the galaxy. If life can thrive across the range we see on Earth, from thermal vents to polar ice, then habitable zones expand enormously. And if life can use entirely different chemistry, then our estimates of habitable worlds are built on assumptions we cannot yet verify, and the universe may be stranger and more inhabited than our models allow. We are, in the most honest sense, still defining the question. And beneath all those questions about where life might exist, there is the oldest one, the one that preceded all of science, that was asked around fires long before anyone had words like biology or astronomy. Are we alone? It is worth sitting with the full weight of what that question contains. Not just whether microbial life exists somewhere in the universe, though that alone would be one of the greatest discoveries in human history, but whether, out there in the hundreds of billions of galaxies, each containing hundreds of billions of stars, there are minds. Creatures who look up at their sky and wonder, who feel something when the dark comes, who tell each other stories, who ask questions they cannot answer. The universe is so vast that the absence of an answer is not the same as an absence of others. Light takes time to travel. Civilizations take time to develop. The signals, if they exist, may be traveling toward us right now, still centuries away from arriving. Or they may have arrived and gone unnoticed, in a frequency or form we did not think to monitor. Or the silence may be real. Life may be so improbable, or intelligence so fragile, that across the entire observable universe, we are the only ones asking. Even as you rest right now, radio telescopes are listening. Probes are crossing the void toward distant moons. Computers are sifting through the signals of 10,000 stars, looking for something that should not be there. The oldest question has no answer yet, but it has never been asked more carefully than it is being asked tonight. And perhaps the most extraordinary thing about that question, about the search, the listening, the careful and persistent wondering, is that it requires something no telescope can detect, no instrument can measure, no equation can fully describe. It requires a mind that is aware it is asking. Consciousness. You are experiencing it right now, not as an abstract concept, not as a word in a science textbook, but as the immediate, undeniable fact of your own awareness. There is something it is like to be you, lying here in the dark, feeling the weight of your body, hearing the quiet sounds of the night. That inner experience, the redness of red, the feeling of warmth, the sense of being a self inside a world is so familiar, it seems to need no explanation. And yet it is the thing science understands least of all. We can map the brain in extraordinary detail. We know which regions activate when you see a face, when you feel fear, when you retrieve a memory or solve a problem. We can watch in real time as electrical signals propagate across billions of neurons, as chemicals flow between synapses, as the entire vast network of your brain hums with coordinated activity. None of that explains why there is something it is like to be you. A brain scan can show activity in the visual cortex when you see a color. It cannot explain why that activity is accompanied by the experience of color, why it feels like something, rather than simply happening in the dark, without any inner witness at all. This gap between the physical process and the subjective experience is what philosopher David Chalmers called the hard problem of consciousness. And it remains, despite decades of neuroscience, philosophy, and even some tentative physics, genuinely unsolved. Some researchers believe consciousness will eventually be explained by neuroscience, that it is simply what certain kinds of information processing feel like from the inside, and that as we understand the processing better, the feeling will become explicable. Others believe something more is needed, a new principle of nature, perhaps, that connects physical processes to subjective experience, in a way our current theories cannot account for. Others go further still, wondering whether consciousness is not produced by the brain, but is instead a fundamental feature of reality present, in some form, wherever information is processed and organized, from the simplest systems upward. No one knows. And the not knowing here is different from the not knowing of dark energy or cosmic inflation, because this mystery is not out there, at the edge of telescopes and particle accelerators. It is right here. It is you. Every night, that consciousness steps aside. Not entirely something continues. Something that can respond to a sudden noise, that will wake you if the temperature drops too low, that keeps your heart beating and your lungs expanding in their quiet rhythm. But the part of you that reads and plans and worries and remembers, that part loosens its hold, and in its place, something else begins. Dreams. In the hours after you fall asleep, your brain does not rest. If anything, certain regions become more active than they are when you are awake. The amygdala, involved in emotion, lights up. The visual cortex generates images. The prefrontal cortex, the seat of logic and self-monitoring, grows quieter, which may be why dreams can be so strange, so willing to accept impossible things as perfectly ordinary. And from all that activity, stories emerge, vivid, sometimes beautiful, sometimes terrifying, almost always strange when examined in daylight. People who exist only in dreams. Places assembled from pieces of real places, rearranged without regard for geography or logic. Emotions more intense than waking life sometimes manages. Why? The honest answer is that we do not know. Some researchers believe dreams are a byproduct of memory consolidation, the brain replaying and reorganizing the experiences of the day, and the dream being the side effect of that replay rather than its purpose. Others think dreams serve an emotional regulation function, allowing the brain to process threatening or difficult experiences in a context where the body is safe and still, rehearsing responses to danger without the danger being real. Some studies suggest that dreams involving fear and threat, which are remarkably common across cultures and across history, may help calibrate the brain's responses to real threats, keeping emotional reactions tuned and appropriate. Others believe dreams are largely noise, the sleeping brain generating activity, and the narrative-hungry mind constructing stories around that activity, the way it constructs patterns in clouds. Random firing, dressed in story by a brain that cannot help but find meaning. What is certain is that you will dream tonight. Something in your brain will generate a world, populate it, and move you through it. And in the morning, most of it will be gone. The purpose of all that vivid, vanishing experience remains, quietly, one of science's most intimate unsolved questions. While you dream, your sense of time dissolves, and even when you are awake, that sense is less reliable than it feels. Think of a moment of sudden shock, a near accident, a sudden loud noise, a moment of genuine fright. Time seems to stretch. Details crystallize. The world slows to a pace that allows you to see individual frames of experience where normally they blur together. Now think of an afternoon spent absorbed in something you love. A conversation, a book, a piece of music that carries you completely away from the clock. Hours compressed to what feels like minutes. You surface, startled by how much time has passed. The same seconds, measured differently. Your brain does not have a single clock the way a watch does. It has many systems that contribute to time perception. Dopamine levels, the rate at which the brain processes new information, the amount of attention being directed to timing itself. When the brain is flooded with stress hormones, processing speeds up and time seems to slow. When you are fully absorbed, the brain devotes fewer resources to tracking duration, and time seems to shrink. This may explain one of the gentler mysteries of aging, why childhood summers seem to stretch forever, while adult years accelerate past. A child encounters so many genuinely new experiences that the brain processes each one richly, creating dense, detailed memories that feel long in retrospect. As life becomes more familiar, more routine, less demanding of full attention, the brain encodes less, and the same duration leaves a smaller trace. But these are hypotheses, not conclusions. The precise mechanics of how your brain constructs your experience of time, how it decides that a minute feels short or long, that a year passed quickly or slowly, remains incompletely understood. Time, which feels so solid and so certain, turns out to be something the brain assembles, imperfectly, from many sources. And sometimes it assembles it wrong in ways that reveal, more clearly than anything else, how constructed the experience truly is. Memory is part of what the brain uses to construct time. The richness of what you remember shapes how long a period of your life feels in retrospect. And memory itself is one of the most counterintuitive things the brain does. It is not recording. It is not storage in the way a hard drive stores data fixed, stable, retrievable, in the same form it was written. Memory is reconstruction. Every time you remember something, you are not replaying a stored experience. You are rebuilding it from fragments, guided by what you currently know and feel and expect. This means memory is malleable in ways that feel deeply wrong. People can remember events that never happened, in detail, with confidence. Researchers have successfully implanted false memories of being lost in a shopping mall as a child, of having met Bugs Bunny at Disneyland, an impossibility. Since Bugs Bunny is a Warner Brothers character, the memories feel real. They carry emotion. They have the texture of genuine experience. And true memories change each time they are recalled. The act of remembering makes a memory slightly susceptible to alteration, to being colored by present mood, by new information, by the questions being asked, reconsolidated back into storage in a slightly different form each time it is retrieved. This is not a flaw. It may be a feature, allowing memories to update with new understanding, to incorporate what you now know into what you once experienced. But it makes the confident certainty we sometimes feel about our memories a more complicated thing than it appears. How the brain encodes an experience, how the firing of neurons during an event becomes a pattern that can be retrieved weeks or years later, is still not fully understood at the mechanistic level. How some memories persist for a lifetime while others fade within hours. Why certain smells or sounds unlock experiences with an immediacy that other cues cannot approach. The neuroscience of memory is rich and progressing, but the complete picture of how your past lives inside your brain remains, in important ways, unwritten. Woven through those memories, shaping how they are encoded and recalled, are the feelings that accompanied them, because emotion is not separate from thought. It is not a separate system that occasionally interferes with the rational brain. It is threaded through everything, through perception, through decision-making, through memory, through the sense of self. But where do emotions come from? The simple answer that they are evolved responses, built by natural selection to guide behavior toward survival, is certainly part of the truth. Fear keeps you away from danger. Disgust keeps you away from contamination. Affection keeps you close to those who matter to your survival and your children's. The broad strokes of this story are well supported, but emotions are stranger and richer than pure survival machinery. They arise in response to music, to mathematics, to the beauty of a landscape that has no bearing on your survival. They can be triggered by something you read in a book, by the suffering of a stranger thousands of miles away, by a dream you half remember. They can persist long after their cause has passed, or arrive in anticipation of something that hasn't happened yet. Some researchers, following the work of psychologist Lisa Feldman Barrett, argue that emotions are not fixed, universal responses, that the brain does not have a discrete fear circuit that activates in response to threats and produces fear identically in every person. Instead, they propose that emotions are constructed, the brain predicting and creating an emotional state based on past experience, cultural learning, and the current state of the body. In this view, emotions are not discovered, they are made. And what they are made of, and why the making feels so immediate and so real, remains one of the most intimate scientific mysteries there is. You have felt an emotion today. You may feel something right now, something quiet and soft as you rest. Whatever it is, its origins run deeper than any equation has yet followed. And sometimes, without warning, without intention, from a place that cannot be located, something new arrives. An idea, a solution, a line of poetry or a mathematical insight or a melody or a design that wasn't there before and then suddenly is complete enough to grasp, arriving as if from outside rather than from within. Creativity is both the most human of things and one of the least understood. The brain, in ordinary waking thought, operates largely through what researchers call the default mode network, a set of regions active during mind-wandering, daydreaming, self-reflection. This network appears to play a central role in creative insight, perhaps because it allows distant, loosely related memories and concepts to drift into contact with each other, forming connections that focused, goal-directed thought would never pursue. This may be why the famous breakthroughs come in the bath, on the walk, in the half-sleep of early morning, not when attention is pressed against the problem, but when it loosens, when the mind is given room to wander in directions logic would not choose. But this description is incomplete. Focused attention is also necessary to evaluate which connections are meaningful, to develop and refine what the wandering mind has found. Creativity seems to involve a conversation between these modes, an oscillation between openness and judgment, between generating and selecting. What neuroscience cannot yet explain is why the generating sometimes produces something genuinely new. Not a recombination of existing elements, though it is always that, at one level, but something that feels, and sometimes is, a step beyond what came before. The source of novelty in human thought remains, at its heart, a mystery. Where ideas come from is a question that ideas themselves have not yet answered. And sometimes the brain does something stranger, still something that briefly makes the present feel like a memory of the present. You step into a hallway you have never entered, and something in you insists you have been here before. Not a vague sense, a vivid, convincing certainty that this moment has already happened, that you know what comes next. And then it passes, in seconds, leaving only the unsettled feeling that something in your perception briefly misfired. Déjà vu? Nearly 2/3 of people experience it at some point, most commonly in adolescence and young adulthood, and most often during moments of mild fatigue or stress. It is fleeting, harmless, and genuinely puzzling. One leading theory suggests it arises from a timing mismatch in the brain's processing. Information from the senses arrives at different brain regions at slightly different times and is normally integrated seamlessly. In déjà vu, the theory goes, some signal arrives at the memory recognition system fractionally before the rest of the processing is complete, triggering a signal of familiarity before the brain has assembled the full picture. The result is the experience of recognition without a corresponding memory to attach it to. Another theory implicates the hippocampus, the brain's indexing structure for memory, briefly pattern matching the current scene to something from the past that resembled it in some partial way, triggering the sense of having been here before without producing the actual memory that would explain it. Neither theory has been conclusively demonstrated. Déjà vu is difficult to study precisely because it is so brief and so unpredictable. It is one of those experiences that arrives only when not expected and vanishes before it can be properly examined. For a few seconds, the present becomes strange. Time folds gently over itself, and then it opens again, and you are back. And the moment that felt remembered was only now, after all. The brain's ability to shape experience extends far beyond perception and memory. It reaches into the body itself in ways that should not be possible and yet are consistently, measurably, remarkably. You are given a pill. It contains no active ingredient. You are told, truthfully or not, that it will ease your pain, and your pain eases. The placebo effect is not imagination. It is not simply people saying they feel better when they don't. Brain imaging shows genuine changes in activity in pain processing regions. The body releases endorphins, its own opioid painkillers, in response to a placebo. Blood pressure changes. Inflammation markers shift. Parkinson's symptoms improve as dopamine production increases in response to a placebo treatment. The expectation of benefit triggers real, measurable, biological changes. The belief that something will help the body becomes, in some meaningful sense, the thing that helps. What makes this stranger still is that it works even when people know they are receiving a placebo. Patients told explicitly that they are taking a sugar pill still experience benefits, in some studies, comparable to those who were deceived. The ritual of treatment, the interaction with a doctor, the act of taking a pill, the context of care carries its own power, independent of the content. Why some people respond strongly and others barely respond at all is unknown. What determines the magnitude of the placebo response, whether it is personality, expectation, genetics, conditioning, is not fully understood. And the precise mechanisms by which the mind reaches into the body's biological processes and changes them through belief alone remain, despite decades of study, incompletely mapped. The body listens to the brain in ways that still surprise us. What it hears and how it decides to respond is not entirely clear. And every night, the brain asks the body for something the body has never been able to refuse, and science has never been able to fully explain. Sleep. It is dangerous from an evolutionary perspective. An animal that sleeps is an animal that is not watching for predators, not foraging for food, not finding mates, not doing any of the things that survival requires. And yet, every animal sleeps or does something that functions like sleep. Flies sleep, fish sleep. Even jellyfish appear to enter a sleep-like state, pulsing less frequently, responding more slowly to stimuli, and catching up when deprived. Something that universal must be essential. But essential for what, precisely, remains genuinely contested. Sleep appears to consolidate memories, the brain replaying and stabilizing what was learned during waking hours. filing experience into long-term storage. It appears to clear waste the glymphatic system, a network of channels that is largely inactive during waking hours, flushes out metabolic byproducts during sleep, including proteins associated with Alzheimer's disease. It appears to regulate emotions. Sleep-deprived people are more reactive, less able to modulate their emotional responses, more vulnerable to anxiety and depression. Each of these functions has evidence behind it. None of them, alone or together, seems to fully account for why sleep is so universal, so non-negotiable, so devastating when withheld. A person deprived of sleep for long enough will die faster than they would die of food deprivation in some conditions. What we are doing for a third of our lives, where we go, what the brain is doing, why it needs the body to be still and the eyes to be closed to do it remains, for all the research devoted to it, a question with pieces of an answer and a great deal still missing. Even as you rest right now, the answer is happening inside you, and you do not need to know it for it to be true. And as you rest, something else is happening, something so gradual it cannot be felt in any single moment, so slow it takes decades to become visible, so universal that every living thing on earth is subject to it in some form. You are aging. Not quickly, not dramatically, but somewhere in your cells right now, at the ends of your chromosomes, tiny protective caps called telomeres are a fraction shorter than they were this morning. Every time a cell divides, and cells divide constantly, replacing worn tissue, healing damage, maintaining the body's vast and intricate machinery, the copying process loses a small amount from each end. The telomeres absorb that loss, protecting the genetic information they bracket, but they have limits. When they grow too short, the cell stops dividing. It enters a state called senescence, alive but no longer contributing, and in some ways actively harmful to the tissue around it. This is one theory of aging, not the only one. Another points to accumulated damage, the slow accumulation of errors in DNA, of oxidative damage from the byproducts of metabolism, of proteins that misfold and clump together rather than performing their functions cleanly. Over years and decades, this damage reaches a threshold where the body's repair systems cannot keep up. Another frames aging as an evolutionary trade-off, that natural selection has little interest in what happens to an organism after it has reproduced, and so has not invested in maintaining the body indefinitely. The resources go into reproduction when they are most useful, and the long-term maintenance of the body is simply not a priority evolution had strong reason to optimize. All of these contain truth. None of them is complete, and the fact that different species age so differently, that a mouse lives 2 years while a Greenland shark lives 4 centuries, while a naked mole rat defies every prediction its size would make, tells us that aging is not a fixed law of nature, but a biological program, or the absence of one. A puzzle with many solutions, none of them yet fully read. Among the most quietly astonishing of those solutions is the one being demonstrated right now in the waters off Greenland. Beneath the Arctic ice, in water so cold and dark that almost nothing moves quickly, a shark glides. It has been gliding for a very long time. The Greenland shark, a slow, heavy, nearly blind creature that drifts through the deep at a pace that would make a leisurely walk seem frantic, grows at a rate of less than a centimeter per year. It reaches sexual maturity at around 150 years of age, and it lives, as best as researchers can determine, for somewhere between 3 and 5 centuries. The oldest individual measured using radiocarbon dating of the lens of the eye, which is laid down in layers like tree rings, and preserves a chemical record of when it was formed, was estimated to be approximately 400 years old. It was alive when Shakespeare was writing. It was alive before the Pilgrims crossed the Atlantic. It may have been alive when the first permanent English settlements were being established in the New World. We do not know why it lives so long. Its metabolism is extraordinarily slow. Its body temperature matches the near-freezing water around it. It may be that the pace of its biochemistry, everything running at a fraction of the speed of warmer, faster animals, simply accumulates damage more slowly. But the full explanation is not clear. The Greenland shark does not know it is a mystery. It moves through its ancient darkness, as it always has, eating slowly, growing slowly, waiting without impatience for whatever the next century brings. Other creatures have found different solutions to the problem of time, not by slowing down, but by doing something that should not be possible at all. In the forests and wetlands of North America, when autumn gives way to winter, the wood frog does something extraordinary. It stops, not in the way a hibernating bear slows down, maintaining a reduced but continuous metabolism through the cold months. The wood frog freezes. Its heart stops beating. Its breathing stops. Ice crystals form between its cells. If you were to pick it up in mid-January and tap it against a hard surface, it would sound solid. And then spring arrives. The ice melts. The heart resumes, at first in halting, irregular beats, then building to its normal rhythm. The frog hops away. How is this possible? Cells are normally destroyed when they freeze the ice crystals that form a sharp, and they tear cell membranes apart. The wood frog prevents this by flooding its tissues with glucose, a natural antifreeze that raises the concentration of solutes inside cells, lowering the freezing point and preventing ice from forming within the cells themselves. The ice forms between cells, in the spaces the blood occupies, drawing water out and causing the frog to shrink slightly, but leaving the cells themselves intact. The details of how the brain, the heart, and the other organs survive months without circulation, without oxygen, without any of the inputs they normally require constantly, are not fully understood. The frog carries a solution to a problem that medicine has been trying to solve for decades: how to preserve living tissue without destroying it. And it carries that solution written in its genome, expressed automatically every autumn. We are still learning to read it. Among the many mysteries of biological time, one stands out for its implications, not just for understanding life, but for understanding disease. Large animals should, by simple mathematics, have more cancer than small animals. They have more cells. Each cell division carries a small risk of a mutation that could lead to uncontrolled growth. An elephant has roughly 100 times more cells than a human, and a bowhead whale has roughly 1,000 times more. Over a lifetime of a century or 2 centuries, those cells divide countless times, each division a small roll of the dice. And yet elephants have very low cancer rates. Bowhead whales, those ancient slow-swimming giants of the Arctic, appear to have even lower rates, living their centuries with a robustness that our own bodies, so much smaller and shorter-lived, cannot match. In elephants, researchers have found a partial explanation. Elephants carry multiple extra copies of a gene called P53, which codes for a protein that acts as a tumor suppressor, detecting damaged DNA and triggering cell death before the damage can propagate. Humans have 1 copy. Elephants may have 20. When their cells are exposed to DNA damage, they die rather than mutate. In whales, the explanation is murkier. Some research points to unusually efficient DNA repair systems. Some suggests metabolic differences that reduce the rate of oxidative damage. Some hints at regulatory mechanisms not yet identified in other mammals. Whatever the answer, it is out there in the biology of creatures that have been solving the cancer problem for millions of years through evolution rather than medicine. If we can learn to read those solutions, the implications for human health are almost beyond calculation. The whale keeps its secret beneath the surface, but we are learning, slowly, to listen. At the surface of the ocean, and in the skies above it, other creatures are demonstrating abilities that seem, by any reasonable accounting, to require senses humans simply do not possess. Birds migrate. This much is obvious. What is less obvious is how, and the more carefully researchers examine the how, the stranger the answer becomes. Certain proteins found in the eyes of migratory birds, cryptochromes, light-sensitive molecules that change their chemical state in response to specific wavelengths, appear to be quantum mechanical compasses. When a photon strikes a cryptochrome molecule, it can produce a pair of electrons in a quantum entangled state. The way that entangled pair evolves depends on the orientation of the molecule relative to Earth's magnetic field. The brain may read this information as something like a visual overlay, a subtle brightening or darkening in the visual field that corresponds to magnetic direction. If this is correct, birds do not merely sense magnetic fields in some vague, passive way. They may see them. They may perceive direction as a quality of their visual experience, as immediate and intuitive as the way you perceive left and right. The hypothesis is supported by experiment but not yet confirmed beyond debate. The quantum mechanics involved are fragile normally. Quantum effects at biological temperatures should be disrupted almost instantly by the warmth and noise of living tissue. That evolution may have found a way to maintain quantum coherence long enough to use it for navigation is itself extraordinary. A bird weighing 30 grams, navigating by quantum mechanics, flying across a continent by a sense that lies beyond human experience. The sky above you right now may be full of them, and we are only beginning to understand what they see. What makes that migration even more extraordinary is that some of the creatures undertaking it have never made the journey before and yet arrive precisely where they are supposed to. The monarch butterfly hatches in the northern United States or Canada in late summer. It has never been south. It has never met a butterfly that went south. The generation that made the southward journey last year died in Mexico. It carries no map, no memory, no cultural transmission of the route. And yet, when the days shorten and the temperatures drop, it flies south-southwest, crossing rivers and mountain ranges and thousands of miles of unfamiliar terrain, arriving at a cluster of Oyamel fir forests in the mountains of central Mexico. Forests it has never seen, in a region it has never visited, where its great-grandparents spent the previous winter. Some of the navigation relies on a time-compensated sun compass. The butterfly adjusts its angle to the sun based on the time of day, maintaining a consistent compass bearing as the sun moves across the sky. There is evidence for magnetic sensitivity as well, and there may be additional cues, chemical, visual, gravitational, that researchers have not yet identified. But none of this fully explains how the destination is encoded, how a butterfly that has never been to Mexico knows not just which direction to fly, but when to stop. How the information persists across generations that have never carried it consciously. The answer is somewhere in the genome encoded in the architecture of the nervous system, expressed in the behavior of an animal with a brain the size of a pinhead. And it is doing something that navigation systems built by the most sophisticated engineering have only recently begun to approach. The monarch is not alone in its impossible knowledge. Across the animal kingdom, creatures are demonstrating navigational abilities that we cannot yet fully account for. Salmon hatch in mountain streams. They spend years in the open ocean, sometimes ranging thousands of miles from their birthplace. And then, at the end of their lives, they return not to any stream, but to the specific stream where they were born. They find it among thousands of tributaries, traveling upstream against the current, navigating by chemistry the precise molecular signature of the water they first knew as juveniles. Sea turtles hatch on beaches, tumble into the ocean, and spend decades at sea. When it is time to lay their own eggs, females return to the beach where they were born, not approximately, not to a nearby beach, but to the specific stretch of sand their bodies first touched. They navigate by magnetic field, using the unique magnetic signature of their natal beach as an address. These abilities feel less like instinct, a word we use when we don't fully understand something, and more like a deep, embodied knowledge of the world that operates through senses and systems we are still mapping. Every autumn, the salmon begin their journey upriver. Every season, the turtles follow their ancient instructions. The ocean and the mountains and the rivers are full of navigators we have not yet learned to fully read. Among the most celebrated of those navigators, and the most personally familiar to humans, is the humble pigeon. Homing pigeons have been carrying messages since at least the time of ancient Egypt. In the First and Second World Wars, they delivered communications across battlefields where every other form of communication had failed, carrying news of survival and calls for help through conditions that prevented human messengers. Some were decorated for valor. Release a homing pigeon hundreds of miles from its loft, in a location it has never visited, in any direction, and it will find its way home. Not approximately, precisely. How? The answer remains genuinely contested after decades of research. Early experiments suggested a sun compass. The pigeon uses the sun's position and an internal clock to determine direction. But pigeons can navigate on overcast days, ruling out the sun as the only cue. A magnetic sense appears to be involved. Magnetite crystals have been found in the beaks of pigeons, and disrupting the magnetic field around them affects their navigation. But surgically removing the suspected magnetic sensors does not eliminate homing ability, suggesting other systems compensate. Olfaction has been proposed, the idea that pigeons build a scent map of their home region, learning the characteristic smell directions of winds arriving from different points of the compass, and using this map to navigate. Some experiments support this strongly, others contradict it. The truth may be that pigeons, like many navigating animals, use multiple redundant systems cross-checking information from different senses, defaulting to alternatives when one source fails. The robustness of the behavior may come precisely from its multiplicity. A pigeon sits on a wire somewhere tonight, its small head turned slightly, reading something in the world that you cannot perceive. It knows where home is. The full explanation of how is still, gently, in flight. The ability of animals to navigate by magnetic fields raises a question that reaches back to the very beginning of human experience, to the moment when one of our ancestors first pointed and made a sound that meant something to beyond another. How did language begin? Not language as a fully formed system, grammar, syntax, recursion, the ability to talk about things that are absent or events that haven't happened yet. But the first step, the first deliberate, shared, meaningful communication between two human minds. Our closest living relatives, chimpanzees, bonobos, gorillas, are capable of remarkable things. They can learn to associate symbols with meanings, to communicate requests, to understand something of another individual's perspective. But the gap between their communication and human language is not a matter of degree. It is structural. Human language allows us to construct, in principle, an infinite number of sentences from a finite set of words to describe anything, to imagine anything, to ask any question. When did this capacity emerge? The fossil record offers indirect clues. The Broca's area of the brain, associated with language production, can be inferred from skull casts, and early Homo sapiens had the anatomy for it. But anatomy is not language. The hyoid bone, which anchors the muscles used in speech, appears modern in fossils more than 100,000 years old. And yet, the earliest clear evidence of symbolic behavior, art, ornamentation, objects that carry meaning beyond their physical function, appears and spreads relatively recently, within the last 100,000 years, in what some researchers call the human revolution. Whether language was the cause of that revolution, or its consequence, whether it emerged gradually over millions of years, or relatively suddenly, is still debated. The first word was spoken and is gone. What it was, and who heard it, we will never know. What we do know is that somewhere in that long history, another sound appeared, one that has no survival value whatsoever, one that is present in every human culture ever documented, that appears in infants before they can speak, that is contagious across a room, that can arrive unbidden in the most solemn of moments, and cannot always be stopped once it starts. Laughter. Other primates laugh or something very like it. Chimpanzees produce a panting sound during play that shares acoustic features with human laughter and serves a similar social function, signaling that what is happening is play, not threat. The evolutionary roots of laughter likely stretch back millions of years to a sound that communicated safety. But human laughter has grown into something more complex. We laugh at incongruity, at the gap between what is expected and what arrives. We laugh at recognition when someone articulates something we have experienced but never named. We laugh at absurdity, at cleverness, at our own embarrassment, at the embarrassment of others, at relief when fear turns out to have been unnecessary. Sometimes we laugh when nothing is funny. Sometimes we cannot explain why. And laughter does things to the body. It releases endorphins. It reduces cortisol. It synchronizes physiological states between people in a room, bringing heart rates and breathing rhythms into something like alignment. A room full of people laughing together is a room full of people whose bodies are briefly becoming more like each other. Why? Organized sound, followed by exhaled breath, should accomplish all of this. Why the particular rhythm of laughter, and no other sound, triggers these cascades remains, in its way, as mysterious as music, which is where we are going next. Music. There is no survival reason for it. It does not find food or build shelter or warn of danger in any direct way. It is, by the coldest evolutionary accounting, unnecessary. And yet every human culture that has ever been documented makes it. Every civilization that has left any trace has left evidence of music. Instruments have been found in archaeological sites more than 40,000 years. Old flutes carved from bone, tuned to specific intervals, played by hands that were otherwise occupied with the business of surviving an ice age. Something in us needs this. Something in us reaches for organized sound the way it reaches for warmth. And what music does to the body is difficult to explain by any theory that treats it as merely pleasant. Music can raise goosebumps, a response called frisson, involving the same physiological pathway as genuine cold or genuine fear, triggered instead by a chord progression or a particular moment in a melody. It can synchronize the heartbeats of people listening together in a room. It can reduce the perception of pain. It can calm premature infants in neonatal units better than certain medications. It can unlock memories in people with advanced dementia who have forgotten almost everything else. A song from childhood returning, complete, when nothing else can reach them. Stroke patients who have lost the ability to produce speech can sometimes still sing. The melody carries the words through a different pathway, one the damage did not reach. Rhythm can help Parkinson's patients move more fluidly, the external beat providing a scaffold that the damaged internal timing system can no longer supply. Why should this be? Why should organized vibrations in the air reach so deeply into the biology of the brain and body? What is the mechanism by which a minor chord evokes something that functions remarkably like sadness, even in people who have never been taught to associate minor chords with sadness? The answers are partial, and the mystery runs deeper than the parts that have been answered. Music is one of the most powerful things humans do, and why it is powerful, what it is actually doing, in the neural and physiological sense, remains one of the most beautiful open questions in science. Woven through music, and through almost everything else that gives a human life its particular texture, is something that resists every attempt to reduce it to chemistry, or evolution, or neural circuitry. Love, not the broad category of affection, but the specific, overwhelming, sometimes completely irrational attachment that human beings form to each other, the bond between parents and children that can outlast reason, the romantic connection that makes ordinary life suddenly luminous, the deep friendship that survives decades and distance and change. Biology offers a partial account. The early stages of romantic love are accompanied by elevated dopamine, which produces something like the euphoria of a drug. Oxytocin, sometimes called the bonding hormone, rises during physical contact and reinforces attachment. Cortisol, the stress hormone, often spikes in early love, which may explain why new love can feel simultaneously wonderful and terrifying. The brain in early romantic love, scanned in an imaging machine, looks somewhat like a brain in the grip of obsessive-compulsive disorder, which perhaps says something truthful about both. But this account, while real, does not feel complete. It describes the chemistry without touching the experience. It says what is happening in the neurons, without reaching the question of why a particular person, of all the people in the world, becomes the one around whom an entire life reorganizes itself. Why loss of love carries a pain that is physically located in the chest, an ache that is genuinely somatic, not merely metaphorical. Why love persists through argument, through change, through the slow transformation of the beloved into someone quite different from the person first loved. Love is woven from memory, imagination, attention, habit, and something else that none of those words adequately names. Its full nature remains one of the most profound mysteries of being alive, familiar to almost everyone, fully understood by no one. And sometimes, in the presence of love, or of loss, or of something so beautiful or so overwhelming that the body does not know what else to do, tears come. Only in humans. Other animals produce tears. Their eyes need the moisture, the lubrication, the protection from debris and infection that tears provide. But emotional tears, Tears produced in response to feeling rather than to physical need appear to be uniquely human. No other animal has been convincingly documented producing tears in response to emotional states. Why did this evolve? The most persuasive hypothesis is that emotional tears are a social signal, a visible, involuntary display of an internal state that is difficult to fake, precisely because it is involuntary. Tears make vulnerability visible. They invite care. In a social species where cooperation and mutual support are essential to survival, a reliable signal of genuine distress, one that is costly to produce falsely, may have been selected for. There is some evidence that tears contain chemical signals that affect the people who encounter them. Research has suggested that the smell of tears, even when their source is not visible, can reduce aggression and sexual arousal in people exposed to them, subtly dampening the threat posed by others and creating space for a different kind of response. But the evidence is still developing. The mechanisms are still being explored, and the full explanation for why only humans weep remains genuinely open. What is not open is the experience of it. You have cried, perhaps in sorrow, perhaps in relief, perhaps in the presence of something so beautiful it exceeded what joy alone could hold. In those moments, the body does something it has done for all of human history, for reasons that science is still working to understand, with an effect that every person who has ever wept knows is real. What tears carry across a face, myths carry across millennia. And perhaps what is most remarkable about myths is not that every culture has them, that alone seems natural enough, but that cultures with no known contact with each other have told, in startling detail, versions of the same stories. Flood myths appear on every inhabited continent. A great deluge, a survivor warned by divine or supernatural agency, a vessel, a remnant of humanity from which the world is repopulated. The story appears in ancient Mesopotamia, in the Hebrew Bible, in the mythology of ancient Greece, in the oral traditions of indigenous peoples of Australia, of North America, of South America, of sub-Saharan Africa. Sky gods, creation from nothing or from chaos, a first man and woman, a trickster figure who steals fire or light or some essential thing from the powerful and gives it to humanity. A land of the dead beneath the world of the living, these patterns repeat, across oceans, across centuries, with a consistency that demands some explanation. Several have been proposed. Some argue for a historical kernel that a real catastrophic flood, perhaps the flooding of the Black Sea around 7,000 years ago, or the dramatic sea level rise at the end of the last ice age, entered human memory and was carried across continents by migrating populations. Others propose that the human mind, everywhere and always, generates certain stories from certain universal experiences, that the fear of flood, the awe of sky, the encounter with death, naturally produces similar narratives across different cultures. Others still look for something deeper, structural patterns in human cognition, shapes that thought naturally takes when trying to make sense of the world, that produce similar myths the way similar environments produce similar animal adaptations. The question of why human minds, across all their diversity, keep returning to the same stories is one that anthropology, psychology, and neuroscience are still exploring together. The stories persist. Their origin remains, like the stories themselves, ancient and not yet fully told. Stories and myths, and the cooperative civilizations that carry them, all of these, depend on something that is, by the standards of the animal kingdom, deeply unusual. We help strangers. Not occasionally, not reluctantly, not only when there is a clear personal benefit. Humans donate blood to people they will never meet. They run into burning buildings for children they have never seen. They give to charitable causes that benefit people on the other side of the world, people of different languages and cultures, people they will never encounter. They feel genuine distress at suffering they are only told about, suffering they cannot see. This is strange. Evolutionary theory predicts cooperation among kin. The closer the genetic relationship, the stronger the motivation to help. It predicts reciprocal cooperation among individuals who will interact repeatedly. You help me today because you expect I might help you tomorrow. These mechanisms are well documented and well understood, but human cooperation extends far beyond them. Experiments show that even young children, before they have been fully socialized into cultural norms of sharing and fairness, spontaneously help strangers, handing something to a person who has dropped it, pointing to something a person is searching for, sharing food with someone who has none. Something in the human mind, present before it has been taught, appears oriented toward the welfare of others. Whether this is a specific adaptation selected for because it strengthened group cohesion in ways that outcompeted less cooperative groups, or whether it reflects something deeper, a moral intuition built into the architecture of human thought, is genuinely debated. What is not debated is that it is real, and that it is one of the most beautiful and most surprising things about the species you belong to. Those cooperative humans built civilizations, and civilizations, across history and across the world, have followed a pattern that no one has yet fully explained. They rise, they grow complex, they reach a peak of sophistication in art, in governance, in technology, in the organization of large numbers of people toward shared purposes. And then, often with a suddenness that surprises archaeologists who study them, they collapse. The Maya built cities with advanced astronomy and mathematics in the jungles of Mesoamerica, and then those cities were abandoned. The Indus Valley civilization constructed remarkably sophisticated urban infrastructure drainage systems, standardized weights and measures, multi-story buildings, and then disappeared, leaving behind a script that has never been deciphered. The Western Roman Empire, which at its height administered a population of 50 million people across millions of square kilometers, fractured over the course of a few generations into smaller, simpler societies that could not read many of the texts their predecessors had written. Why? Climate change has been implicated in several collapses, droughts that disrupted agriculture and destabilized food supplies, rapid shifts in rainfall patterns that made once productive regions unable to support large populations, invasion, war, internal conflict, inequality that grew until cooperation became impossible, the exhaustion of natural resources. All of these have played roles in specific cases. But there is no single explanation that fits all cases, and there is something about the pattern, the rise, the complexity, the sudden simplification that suggests forces more general than any particular drought or invasion. Whether civilizations carry within their complexity the seeds of their own undoing, and whether anything in human organization can escape that pattern, is a question historians, archaeologists, and social scientists continue to ask. We are living inside a civilization right now. It is impossible, from the inside, to read its arc. The curiosity that built those civilizations, that drove humans to plant crops and build cities and send probes to the edges of the solar system and spend long nights listening to the sky, is itself one of the most interesting, unexplained features of the human mind. We are curious about things that have nothing to do with our survival. A physicist spends 30 years studying the behavior of particles that no practical technology will ever require an understanding of. A poet spends decades refining the sound of language in ways that carry no material benefit. A child, given a few free hours, will ask questions until the adults around them have exhausted every answer they have. The drive to know, not just to know what is useful, but to know for its own sake, to understand the structure of things that have no bearing on immediate survival, appears to be built into the human mind at a level that precedes culture and education. Why? The survival-based explanation that curiosity led early humans to explore new environments, find new food sources, develop new tools accounts for some of it. But it doesn't account for the mathematician pursuing pure mathematics for its own beauty, or the astronomer spending a lifetime cataloging stars in galaxies that will never affect human life in any measurable way. Something in the human mind finds intrinsic reward in understanding. The feeling of making sense of something, the small inner satisfaction of a question answered, even a trivial question, even a question no one else cares about, is experienced as genuinely good. In the same way, food or warmth is experienced as good. Why the mind is built this way, why understanding feels like something worth having, is a question that the curious human mind is, characteristically, deeply curious about, and does not yet know the answer to. That curiosity, expressed across 1 million campfires and 1,000 generations, produce something else that appears to be uniquely and universally human. Stories. Not just communication, not just the transmission of useful information from one mind to another. Stories. Narratives with structure and character and consequence and meaning. Accounts of things that never happened, peopled by characters who never existed, that nevertheless carry truths that factual accounts sometimes cannot reach. Every human culture tells stories, and not only practical stories, not only accounts of where the water is, or which plants are safe to eat. Stories about love and loss, about heroes and failures, about the nature of good and evil, about what happens after death. Stories that exist purely to be told and heard, that serve no obvious survival function, and that people will stay awake past midnight to finish. Children, before they can fully understand the words, demand stories. Adults, across every culture and every historical period, organize significant portions of their leisure time around stories, around novels and films and theater and myths and games that are, at their heart, elaborate, collaborative storytelling. Why? One possibility is that stories serve as a kind of flight simulator for the mind, allowing us to rehearse emotional and social situations safely, to practice responses to challenges we haven't yet faced, to inhabit perspectives not our own. Another is that stories bind communities by giving people shared points of reference, shared values, shared understanding of what is heroic and what is shameful. But stories go beyond either function. They carry people into experiences that have no practical application and leave them changed in ways they cannot fully articulate. They do something to the mind that reality alone does not do. What? Exactly. That something is why the shaped narrative reaches places that raw experience does not remains one of the quieter mysteries of what it means to be human. And there is one more mystery that belongs to this middle stretch of our journey tonight. One that sits at the intersection of nature and mind, between the physics we have been exploring and the biology we are moving through. Ball lightning. For centuries, people have reported seeing it, A glowing sphere, sometimes the size of a grape, sometimes the size of a basketball, appearing during or after a thunderstorm, drifting slowly through the air, sometimes passing through closed windows without breaking them, sometimes floating through rooms, sometimes hovering for several seconds before vanishing, silently or with a soft pop. For most of that history, the reports were dismissed. Ball lightning was the kind of thing that happened to other people in other centuries, and could surely be explained by optical illusions, by the after-images left on the retina, by ordinary lightning, by the overactive pattern recognition of frightened minds. Then, in 2012, a team of researchers in China, who were studying ordinary lightning with spectrographic equipment, accidentally captured ball lightning on camera and analyzed its spectrum. It contained the spectral signatures of silicon, iron, and calcium elements found in soil, suggesting that the lightning strike had vaporized minerals from the ground, and that the resulting plasma ball had remained coherent, briefly, before dissipating. This is one hypothesis. There are others involving microwave radiation trapped by ionic fields, or quantum mechanical effects, or electromagnetic structures that our current theories have not fully predicted. None of them accounts for all the reported behaviors, particularly the ability to pass through glass, or to float indoors in ways that seem to defy the airflow patterns that would disperse a plasma. Ball lightning remains real, rare, poorly understood, and genuinely mysterious, a ghost in the physics that ordinary lightning does not entirely explain. A small, glowing puzzle, drifting quietly through the history of science, waiting for the theory that will finally describe it. There are other moments when the Earth itself produces light in ways that should not, by ordinary understanding, be possible. In the hours before a large earthquake, sometimes minutes before, sometimes days, witnesses have reported seeing things in the sky that no storm is producing. Columns of pale blue light rising from the ground along fault lines. Flickering luminescence spreading low across the horizon. Balls of light hovering above cities before the ground begins to move. Photographs and videos taken during recent major earthquakes have captured them, not as rumor, not as misremembering, but as documented phenomena requiring explanation. What causes earthquake lights? The most widely discussed theory involves the piezoelectric properties of certain rocks. When rocks containing quartz crystals are subjected to intense pressure, the kind that builds along fault lines in the weeks and days before a rupture, they can generate electrical charges. Those charges, rising through the rock and into the air above, might ionize the atmosphere, causing it to glow the way a neon tube glows when electricity passes through it. Another hypothesis proposes that the movement of charged particles through narrow channels in stressed rock creates a kind of underground electrical current, which can emerge at the surface and produce light through mechanisms similar to ball lightning. Neither explanation accounts for all the observed varieties. The lights appear in different forms in different earthquakes, at different times relative to the rupture, in different geographical settings. Some appear only at the surface, others seem to rise high into the sky. Some last seconds, others have been reported to persist for minutes. They are real, they are rare, and they carry within them a hint that the solid ground beneath you is more electrically alive than it appears, that the rock you stand on is not inert but dynamic, building and releasing energy in ways that occasionally light up the sky. Below that ground, in chambers that dwarf the largest human constructions, pressure builds in ways that geology can measure, but not always predict. Volcanoes. Most volcanic eruptions are, by geological standards, modest. Lava flows from a vent, Ash blooms into the atmosphere, and the surrounding landscape is reshaped over weeks or months. These are dramatic, sometimes devastating, but they are within the range of what human civilization has learned to anticipate and, to some extent, manage. But somewhere in the geological record, there are eruptions of a different order entirely. Events that released energy 1,000 times greater than the largest eruption in recorded human history. Events that loaded the stratosphere with so much ash and sulfur dioxide that global temperatures dropped for years, that harvests failed across continents, that famines followed, that the world was briefly and profoundly altered by the violence of a single geological event. The eruption of Mount Tambora in 1815 killed tens of thousands directly, and is estimated to have contributed to the death of more than 100,000 more through the famine and disease that followed. The year 1816 became known in parts of Europe and North America as the year without a summer. Crops failed in June, snow fell in July, and the disruption rippled outward through economies and lives for years. And Tambora was not the largest. The eruption of Toba, approximately 74,000 years ago, may have been so catastrophic that it drove the human population to the edge of extinction, reducing our ancestors to perhaps a few thousand individuals, scattered across the globe, surviving what may have been a volcanic winter lasting years. What triggers a supervolcanic eruption? The pressure of accumulating magma, certainly. The saturation of dissolved gases that, when the pressure is released, drive explosive expansion, the way carbon dioxide drives the eruption of a shaken bottle. But the precise tipping point, why some volcanoes build pressure for centuries without erupting, and others release catastrophically, is not yet predictable. The instruments monitoring the world's great volcanic systems measure seismic activity and ground deformation and gas emissions, and they provide early warning of increasing unrest. But the moment of transition from unrest to eruption remains, for the largest systems, genuinely uncertain. Beneath Yellowstone, beneath the Campi Flegrei caldera in Italy, beneath the Taupo volcanic zone in New Zealand, magma moves in the dark, patient, unmeasured by anything except the instruments above it. When it will move again, and how it will move is written in a language geology is still learning to read. Long before any of those volcanoes existed, the surface of the Earth was doing something that no other planet in the solar system has managed to replicate. It was moving, not drifting, not slowly eroding, actively moving, in great slabs of rock called tectonic plates, grinding against each other at their boundaries, diving beneath each other in deep ocean trenches, pulling apart to open new oceans, crashing together to raise mountain ranges. The surface of the Earth is not a fixed shell, but a set of enormous moving pieces, driven by convection currents in the hot mantle below, cycling material between the surface and the deep interior over timescales of hundreds of millions of years. This cycling is not merely geological scenery. It is, many researchers believe, essential to the long-term habitability of the planet. The carbon cycle, the process by which carbon moves between the atmosphere, the oceans, living things, and rocks, depends on plate tectonics to close its loop. Without tectonic activity to return carbon-bearing rocks to the interior, where they are heated and their carbon released back into the atmosphere through volcanoes, the cycle would eventually stall. The atmosphere would either fill with carbon dioxide or be stripped of it, and the regulation of temperature that has kept Earth habitable for 4 billion years would fail. Mars has no active plate tectonics. Neither does Venus. Neither does any other body in the solar system that we know of. The conditions that produced plate tectonics on Earth, The particular combination of interior temperature, water content in the mantle, and crustal composition were either extraordinarily specific or extraordinarily lucky, or both. Whether plate tectonics is rare in the universe, and whether its absence on other planets explains their uninhabitability, is a question that planetary science is only beginning to be equipped to answer. The ground shifting beneath your feet is one of the rarest gifts the universe has given to life, and why Earth received it when its neighbors did not is still an open question. Earth received something else its neighbors did not, or at least did not keep. Something so ordinary that it covers 70% of the planet's surface, fills the clouds above you, moves through your body in every breath and every heartbeat, and is so essential to life that no organism we have found can survive long without it. Water, where it came from, is genuinely uncertain. The young Earth, formed from the collision and accretion of rocky material close to the Sun, should have been largely dry. The region of the solar system where Earth formed was too warm for ice to condense the water that exists in the inner solar system today, was not, for the most part, present when the planets were being assembled. Something brought it later. The leading candidates are asteroids and comets. Carbonaceous chondrite asteroids, some of the most ancient and chemically primitive objects in the solar system, contain water locked in their minerals, and the ratio of hydrogen isotopes in some of Earth's water matches the ratio in these asteroids. Comets also carry water ice, and the early solar system was bombarded intensely by both. But the hydrogen isotope ratios in comets from the outer solar system often don't match Earth's water as precisely as the asteroidal match. The picture is complicated by the fact that not all comets are the same, and that some researchers believe a significant fraction of Earth's water may have been present from the beginning, incorporated into the building blocks from which the planet formed, or outgassed from the interior over geological time. The oceans you carry in your cells, the salt water in your blood that echoes the composition of ancient seas, arrived here by a journey that is still being reconstructed. Every molecule of water you have ever drunk has a history stretching back to the early solar system, and that history is still being written. While water shaped the surface of the Earth, something was happening on its nearest companion that has puzzled every scientist who has looked carefully at it. The moon has two faces, and they are completely different from each other. This is not a metaphor. The side of the moon that faces Earth, the face you see when you look up on a clear night, is covered with large dark plains called maria, vast ancient lava flows that filled enormous impact basins billions of years ago. The surface is relatively smooth, geologically speaking. Craters interrupt it, but between them, the dark plains spread for thousands of kilometers. Turn the moon around. Look at the side that permanently faces away from Earth, the side that no human eye saw until a Soviet spacecraft photographed it in 1959, and you find an almost completely different world. No maria, almost no smooth plains. Instead, a surface of relentless, dense, overlapping craters, higher in elevation on average, and covered by a thick crust that appears to have prevented the lava eruptions that created the maria on the near side. Why the difference? The most widely discussed explanation involves the asymmetric thermal history of the early moon. Earth, warm and nearby, may have kept the near side warmer than the far side during the period when the moon's crust was solidifying, allowing the crust on the near side to remain thin enough for volcanic eruptions to break through, while the far side developed a thicker, more resistant crust. Another hypothesis involves an ancient collision, a second, smaller moon that existed briefly in Earth's orbit, and eventually merge slowly with the primary moon, adding material to the far side and explaining its elevated, heavily cratered surface. Neither explanation is fully satisfying. The same moon, the same origin, the same 4 billion years of history, and yet two faces as different as if they belong to different worlds. The moon that lights your nights carries a mystery on the side you cannot see. Beneath the earth that the moon orbits, deeper than any drill has ever reached, deeper than any direct observation has ever penetrated, something moves in the dark. Liquid iron, primarily with nickel and traces of other elements, swirling in slow, vast convective currents, driven by heat from the still cooling interior and by the rotation of the planet itself. This motion generates electric currents, and those electric currents generate a magnetic field that extends far out into space around the planet, deflecting the stream of charged particles flowing outward from the sun. Without this field, that solar wind would gradually strip away the atmosphere. Water vapor would be lost to space. The surface would be bathed in radiation. Mars lost its magnetic field billions of years ago, and Mars lost most of its atmosphere, and Mars became the dry, thin-aired, radiation-exposed world we see today. Earth kept its field, and yet we do not fully understand how. The process that generates it, called the geodynamo, is understood in broad outline, but the details are deeply difficult. The behavior of liquid iron at the temperatures and pressures of the outer core is not well characterized experimentally. The conditions are too extreme to reproduce in laboratories. Computer simulations of the geodynamo are improving, but they cannot yet capture the full complexity of the real system, and they make predictions that sometimes disagree with observations. Why the field fluctuates in strength, why it has weakened by roughly 10% in the last 150 years, and whether that weakening is the beginning of something larger or a normal fluctuation is not fully understood. The engine at the center of the Earth runs reliably enough to have sustained life for billions of years. Its detailed workings remain, at the scale of our instruments, partly hidden, and sometimes that engine does something far more dramatic than fluctuate. It reverses, recorded in the magnetic minerals of ancient rocks aligned to the prevailing field at the time they cooled and solidified, preserving a permanent record of the field's direction, like a fossil compass, is the unmistakable signature of a planet whose north and south magnetic poles have switched places hundreds of times in geological history. The last full reversal happened approximately 780,000 years ago. Before that, reversals occurred at intervals ranging from tens of thousands to millions of years, without apparent regularity. The timing seems almost random. What triggers a reversal? The leading hypothesis involves instabilities in the flow patterns of the liquid outer core turbulence in the geodynamo that causes the orderly pattern of convection to break down, allowing the field to weaken and reorganize in the opposite direction. But the specific conditions that produce this instability and why it happens when it does, rather than at other times, are not understood. What happens during a reversal is also not fully clear. The field does not simply flip instantaneously. It weakens, possibly over thousands of years, and during that weakening period the field may become complex and patchy, multiple magnetic poles appearing in unexpected locations, the protective shield thinning significantly. Some researchers have speculated that this could expose the surface to elevated cosmic radiation, potentially affecting ecosystems and even driving evolutionary change. Others argue the effects would be modest, that the atmosphere itself provides significant radiation protection even without a strong magnetic field, and that life has survived many previous reversals without obvious catastrophic effects. The north that your compass points to right now is a temporary arrangement. At some point in the future, perhaps soon by geological standards, perhaps not for millions of years, it will point south. And the reason it changes is still written in a script we are learning to decipher. While the magnetic poles drift and reverse on scales of thousands of years, the climate shifts on comparable timescales in patterns that have left their marks carved across entire continents. Ice age. For the past 2.5 million years, Earth has cycled repeatedly between cold glacial periods when ice sheets extended across much of North America and Europe, and the global average temperature dropped by several degrees, and warmer interglacial periods, like the one we currently inhabit. The cycle has not been perfectly regular, but it has been persistent glaciation, advancing, retreating, advancing again, carving valleys, and depositing moraines, and sculpting landscapes that humans have lived in ever since. What drives these cycles? The most widely accepted framework involves the Milankovitch cycles, periodic variations in Earth's orbit, and axial tilt that alter the distribution of sunlight, reaching the planet across different latitudes and seasons. When these cycles combine in particular ways, reducing summer sunlight at high northern latitudes, snow that falls in winter fails to melt completely through summer, accumulates year over year, reflects more sunlight back into space, and cools the planet further in a self-reinforcing cycle. But the Milankovitch cycles alone do not fully account for the pattern of ice ages observed in the geological record. The cycles have been running for much longer than the ice ages themselves. Something about the last 2.5 million years made the climate particularly susceptible to glaciation, possibly the closing of the Isthmus of Panama, which altered ocean circulation, or the slow uplift of the Tibetan Plateau, which changed atmospheric patterns, or changes in the concentration of greenhouse gases that preceded and accompanied the glaciations. The ice ages shaped human evolution, driving our ancestors through environmental pressures that may have accelerated the development of intelligence, language, and cooperation. The world we inhabit, its coastlines, its river valleys, its soil composition, was profoundly shaped by the advance and retreat of ice that ended only about 12,000 years ago. What set those clocks running, and what will ultimately stop them, is a question that climate science continues to refine, but has not yet fully answered. At 5 moments in Earth's history, the ice and the climate and the ordinary processes of geological and biological change were interrupted by something more sudden and more final: mass extinction. Events in which the majority of species alive, at the time in some cases, the vast majority, were extinguished over geological timescales that, while long by human standards, were catastrophically brief by the standards of evolution. The background rate of extinction is low species disappear, but slowly, as environments change and competitors arise. In a mass extinction, something overrides that background rate catastrophically, and the diversity of life on Earth is reduced to a fraction of what it was before. The most famous is the End Cretaceous extinction, 66 million years ago, in which the non-avian dinosaurs disappeared, along with roughly 3/4 of all species alive at the time. The evidence for a large asteroid impact an iridium-enriched layer in the geological record, a massive crater beneath the Gulf of Mexico, is compelling and widely accepted. The impact would have triggered firestorms, a global winter of ash and dust blocking sunlight, and the collapse of food chains from the bottom up. But even that extinction is not simple. Volcanic activity from the Deccan Traps in what is now India was also occurring at the same time. releasing enormous quantities of carbon dioxide and sulfur dioxide over hundreds of thousands of years. Some researchers believe the volcanic stress was already destabilizing ecosystems before the asteroid struck, and that the combination was more devastating than either alone would have been. Earlier extinctions are murkier still. The end Permian extinction, the greatest in Earth's history, eliminating perhaps 96% of marine species and 70% of terrestrial vertebrate species, may have involved a combination of massive volcanic eruptions, ocean acidification, global warming, and oxygen depletion, all interacting in ways that are still being untangled from the rock record. Every extinction cleared the stage. Every extinction allowed the survivors, the ones with the right combination of luck and flexibility and resilience, to radiate into the emptied ecological space. We are the descendants of survivors. Our existence depends on losses almost beyond imagining. And what, precisely, drove those losses is still, in important ways, a story being read from rock, beyond the rock, beyond the atmosphere, beyond the orbit of the last planet. The solar system wears a crown. Saturn, even among the 8 planets, it stands apart, not in size, though it is vast, second only to Jupiter, but in what surrounds it. Rings. Vast, luminous, impossibly thin rings of ice and dust and rock, extending outward for hundreds of thousands of kilometers from the planet's equator, catching sunlight and scattering it back in the particular blue-white shimmer of water ice. From a distance, they look permanent, ancient, as fixed as the planet itself. They may not be. Data gathered by the Cassini spacecraft during its final years in orbit around Saturn suggested something unexpected. The rings are remarkably clean, bright and white, in a way that ancient rings should not be, given the steady rain of interplanetary dust that darkens everything in the solar system over time. The ring material appears to be young, perhaps only 100 million years old, perhaps less. In geological terms, in cosmic terms, this is recent. The dinosaurs still walked the Earth when Saturn's rings may have formed. If this is correct, then the rings were not there when the solar system was young. Something created them relatively recently, perhaps a moon that wandered too close to Saturn and was torn apart by tidal forces, its icy interior shattered and spread into the disk we see today. Perhaps a comet or asteroid that strayed into Saturn's influence and met a similar fate. And they will not last. Cassini also measured ring rain, a shower of charged particles and water molecules falling from the rings into Saturn's atmosphere, eroding the rings at a rate that suggests they may vanish within 100 million years. We are seeing them at a particular, perhaps fleeting, moment in the solar system's long history. We live in the brief era when Saturn wears its crown. That we are here to see it at all may be one of the solar system's quieter coincidences. While Saturn's rings drift slowly inward, another planet rolls through space in a way that no explanation has yet fully accounted for. Uranus. Every other planet in the solar system spins on an axis roughly perpendicular to the plane of its orbit, tilted a little, some more than others, but generally upright, in relation to the direction of their travel around the Sun. Uranus spins on an axis tilted 98 degrees from vertical. It rolls through space on its side, like a ball being pushed along a floor, its poles taking turns pointing almost directly at the Sun over the course of its 84-year orbit. The most widely accepted explanation is a collision, a massive impact early in the solar system's history, when a body roughly the size of Earth struck Uranus and knocked it onto its side. But this explanation carries problems. Such a collision should have left behind a ring of debris that eventually coalesced into moons, but Uranus's moons orbit in the same tilted plane as the planet's equator, suggesting they formed after the tilt occurred, from material already in orbit around the tilted planet. The collision hypothesis requires careful modeling to produce this outcome. An alternative proposes not one massive impact, but a series of smaller ones, gradually tipping the planet over time. Another invokes gravitational interactions with a massive planet that no longer exists, a fifth giant that was ejected from the solar system in the chaotic early period of planetary rearrangement. Uranus sits at the edge of what our spacecraft have explored. Voyager 2 flew past in 1986, spending only a few hours in its vicinity before continuing outward. Everything we know about Uranus from close range comes from those few hours of data. A dedicated mission to Uranus is among the highest priorities identified by the planetary science community, a mission that could reveal why it rolls, what lies in its strangely calm atmosphere, and whether its small, dark moons hide secrets we have not imagined. Until then, it rolls on, tilted, patient, and unexplained. Its neighbor in the outer solar system presents a different kind of mystery, not in its orientation, but in its history. Venus is nearly the same size as Earth, the same mass, the same density, formed at roughly the same distance from the Sun, from roughly the same materials. In the earliest period of the solar system, Venus and Earth may have been strikingly similar rocky worlds with liquid water, moderate temperatures, and the potential for chemistry to grow complex. Today, Venus has a surface temperature of 465 degrees Celsius, hot enough to melt lead. Its atmosphere is 90 times denser than Earth's, composed largely of carbon dioxide, with clouds of sulfuric acid. No spacecraft has survived on its surface for more than a few hours, and it spins backwards. While Earth and most other planets rotate in the same direction, they orbit the Sun counterclockwise when viewed from above the solar system's north pole. Venus rotates clockwise, and it does so extremely slowly. A single Venusian day lasts longer than a Venusian year. The Sun, from the surface of Venus, rises in the west and sets in the east. Why? One possibility is a massive impact early in Venus's history that reversed its spin. Another is that tidal interactions with the Sun, acting over billions of years on Venus's thick atmosphere, gradually transferred angular momentum in a way that first slowed the rotation and then reversed it. A third possibility involves resonance, the gravitational influence of Earth, which Venus passes relatively close to every 19 months, slowly reshaping its rotation over cosmic time. What happened to Venus's water, if it had water, and why its climate diverged so dramatically from Earth's despite such similar origins, is one of the most pressing questions in planetary science. Because if Venus was once habitable and became this, understanding why matters enormously for how we think about the future of our own world. At the edge of the solar system, in the cold and dark far beyond Neptune, something is always moving, something vast and slow, and almost entirely invisible. The largest planet in the solar system is not Jupiter. It is what Jupiter floats within. When Jupiter and Saturn were young, their enormous gravitational influence scattered smaller bodies outward, flinging comets and planetesimals into the far reaches of the solar system, populating the distant regions of space with trillions of icy objects in a vast, spherical shell surrounding the entire solar system. This shell is called the Oort cloud. Its inner edge may begin tens of thousands of astronomical units from the Sun. Its outer edge may extend a quarter of the way to the nearest star. No spacecraft has ever reached it. No telescope has ever directly observed an object within it. We know it exists only because comets arrive from all directions, including from steep angles well above and below the plane of the solar system directions, that make sense only if there is a roughly spherical reservoir of icy bodies at enormous distances, sending visitors inward when gravitational perturbations from passing stars, from the galactic tide, nudge them out of their distant orbits. How many objects does it contain? Perhaps 1 trillion, perhaps more. What are their compositions? Similar, presumably, to the comets it sends us: water ice, frozen gases, complex organic molecules. Are there objects larger than expected, lurking unseen at those distances? The Oort cloud is the solar system's outermost frontier, a ghostly, enormous, entirely inferred structure surrounding everything, carrying within it the leftover material of the solar system's formation, patient and cold, and waiting for the next nudge that will send one of its members on a long, slow journey inward toward the warmth of the sun. Closer in, where sunlight is stronger and human spacecraft have ventured, the moons of the outer planets have turned out to be among the most surprising places in the solar system. Not dead, geologically frozen worlds, but active, warm, and in some cases potentially harboring the conditions for life. Europa, one of Jupiter's 4 large moons, is covered in a shell of water ice. Beneath that shell, kept liquid by the gravitational kneading of Jupiter's immense tidal forces, lies a global ocean. An ocean of liquid water, in contact with a rocky seafloor, heated from below by tidal friction, perhaps containing the chemical gradients that on Earth sustain life in the complete absence of sunlight. The Hubble Space Telescope has observed what appear to be plumes of water vapor erupting from Europa's surface, suggesting that the ocean below occasionally vents directly into space, the way Enceladus does. If those plumes are real, a spacecraft flying through them could sample the ocean without ever needing to drill through the ice. What lives in Europa's ocean, if anything does, is unknown. The ocean has been liquid, in some form, for billions of years. The chemistry appears right. The energy sources appear present. Whether that is sufficient for life to arise, or whether life requires something more specific that Europa may or may not have, is the question that missions like Europa Clipper, currently en route, are designed to begin answering. The answer, when it comes, will be one of the most significant in the history of science. And it has not come yet. The question of what stirs beneath alien ice is not limited to Europa, because Saturn has a moon that is, in its own way, even more immediately promising. Enceladus is small, only 500 kilometers across, a world you could drive across in a few hours. It should be frozen solid, a geologically dead ice ball, too small to retain any internal heat. And yet, when Cassini flew past it, the spacecraft detected geysers erupting from a series of parallel fractures near the South Pole, the tiger stripe shooting plumes of water vapor, ice crystals, and organic molecules hundreds of kilometers into space. The plumes confirmed what the tidal heating from Saturn's gravity implied. Enceladus has a liquid water ocean beneath its ice, and the chemistry of the plumes was remarkable. They contained salts, suggesting the water had been in contact with rock. They contained hydrogen, suggesting hydrothermal activity, water reacting with hot rock at the seafloor, in the same way that hydrothermal vents on Earth sustain entire ecosystems of organisms that have never seen sunlight. They contained complex organic molecules, including compounds that on Earth are associated with biological processes. None of this proves life, but it checks the boxes that astrobiologists have identified as necessary, and perhaps sufficient, for life as we know it to arise. What drives the geysers, precisely what process links the ocean floor to the surface vents, is not yet fully understood. The internal structure of Enceladus, the nature of the seafloor, the chemistry of the water at depth, all of this remains to be measured by missions that have not yet been built. For now, the geysers rise and fall in the dark, carrying their cargo of ocean water into space, offering it to any passing instrument willing to catch it. And the question of what the ocean below contains drifts quietly upward with every plume. Further from Saturn, in an orbit that takes it nearly 16 Earth years to complete, there is a moon whose surface looks, in some unsettling ways, more like Earth than any other place in the solar system. Titan. It has a thick atmosphere, thicker than Earth's. In fact, though composed of nitrogen and methane rather than nitrogen and oxygen, it has weather. Clouds form and rain falls. Not water but liquid methane, pooling on the surface in lakes and seas that the Cassini spacecraft mapped over years of flybys. Rivers of methane carve channels through water ice rock. Dunes of organic material accumulate in equatorial regions. Wind reshapes the landscape. In all the ways that matter for the surface processes that make a world geologically active and visually familiar, Titan is the most Earth-like world we know of beyond Earth itself. But methane in an atmosphere does not last. Sunlight breaks it down. The methane that Titan's atmosphere contains today should have been depleted long ago if nothing were replenishing it. Something keeps the methane cycle running. Something feeds the lakes. Something replaces what sunlight destroys. What? Cryovolcanism. Volcanic activity in which the erupting material is water, ice, or methane rather than molten rock is one candidate. Some models suggest that Titan's interior contains enough heat to drive such activity, pushing methane from a deep reservoir toward the surface through vents and fissures. But no cryovolcano has been definitively identified on Titan's surface. And there is another possibility, one that researchers are careful not to overstate, but cannot entirely set aside. On Earth, methane is produced in enormous quantities by biological activity. Methane is a biosignature. If life exists on Titan, not life as we know it, not water-based, but life built on liquid methane, using it the way Earth life uses water, it might be producing methane. It might be the hidden pump that keeps the cycle running. The Dragonfly mission, a rotorcraft lander currently in development, is scheduled to reach Titan in the 2030s. When it does, it will sample the surface, analyze the chemistry, and begin to answer the questions that Cassini could only pose from above. Until then, Titan's methane cycles in the cold dark, fed by a source we have not yet found. Closer to the sun, on a world whose surface has been studied in more detail than any other beyond Earth, the signs of an ancient, different world are everywhere. Mars. Valley networks carved by flowing water stretch for thousands of kilometers. River deltas spread across ancient crater floors. Layered sediments that could only have been deposited by standing bodies of water record a planet that was, long ago, genuinely wet. The Curiosity rover has driven through what was once the bed of a lake, finding mudstones and minerals that on Earth form only in the presence of long-standing, relatively neutral water hospitable to life as we know it. Something happened to that world. Its magnetic field weakened, stripped of its protection by an inner dynamo that failed for reasons still debated. Solar wind began to erode the atmosphere. The climate cooled. The water first, the liquid surface water. Then much of the atmospheric water vapor was lost. The rivers stopped flowing. The lakes dried. The planet that might, for hundreds of millions of years, have had the conditions for life, became the cold, dry, dusty world we visit today. Where the water went is still being mapped. Some is locked in ice at the poles. Some appears to be frozen in the subsurface. Some, a significant fraction, is gone, lost to space over billions of years. Whether any water remains liquid today, deep underground where geothermal heat might sustain it, is uncertain. And whether, during the long wet period of early Mars, something lived in those lakes and rivers, something simple, microbial, ancient, is the question that every Mars mission has been designed, in some sense, to approach. We have not found it. We have not ruled it out. The dry riverbeds of Mars hold either the most important silence in science, or an answer we have not yet learned to find. There is something quietly astonishing about the fact that the universe can be described at all, not approximately, not loosely, in rough outlines that capture the general shape of things, but with precision, with equations that predict the behavior of matter and energy to 10 or 15 decimal places, that describe the arc of a planet, or the decay of a particle, or the bending of light around a massive object, with an accuracy that exceeds the finest measurements humans have ever been able to make. Mathematics is a human invention. Symbols drawn on paper, or pressed into clay, or arranged in the mind, a language built from axioms and rules, extended by logic and imagination into structures of extraordinary complexity and beauty. And yet this invented language, this purely abstract construction, maps onto the physical universe with an uncanny precision that no one has been able to explain. The physicist Eugene Wigner called it the unreasonable effectiveness of mathematics. Why should the universe be mathematical at all? Why should the deep structure of reality, the behavior of particles, the geometry of space-time, the dynamics of fields be expressible in terms of equations that humans can write down and manipulate and solve? Some researchers believe mathematics is not invented, but discovered that mathematical truths exist independently of human minds, that we are not creating them but finding them, the way an explorer finds a mountain that was always there. In this view, the universe is mathematical because mathematics is the fundamental structure of reality, and physical laws are simply the particular mathematical structures that our universe instantiates. Others argue that mathematics is a product of human cognition, shaped by the same evolutionary pressures that produced every other aspect of human intelligence, and that its effectiveness is not mysterious. We developed mathematical thinking because it helps us navigate a world that has regular patterns, and those patterns are what mathematics describes. Neither answer is fully satisfying. The mystery is not just that mathematics is useful, but that it is useful in domains so far from any evolutionary pressure in quantum field theory, in the geometry of curved spacetime, in the abstract algebra of particle physics, that no story about practical origins can account for it. The universe speaks in a language we invented, and we still don't know why it knows our words. Within that mathematical language, certain numbers appear, certain specific values for the fundamental constants that determine how the equations play out in reality, and those values are simply given. They are not derived from deeper principles. They are measured with extraordinary precision and then written into the equations as facts about the universe that the equations themselves cannot explain. The speed of light, the gravitational constant, the mass of the electron, the fine structure constant, which governs the strength of electromagnetic interactions, the cosmological constant related to dark energy. These numbers have values. Those values determine everything: the size of atoms, the lifetime of stars, the structure of molecules, the possibility of chemistry, the existence of life. And no theory currently available explains why they have the values they do. This is not for lack of trying. String theory, in its various formulations, predicts a vast landscape of possible universes, each with different values for the constants, and some versions suggest that the values we observe are simply one point in an enormous space of possibilities, with no deeper reason to prefer them, except that they allow observers to exist. But this anthropic reasoning, while logically coherent, does not feel like an explanation in the way that most scientific explanations do. Others hope that a deeper theory, something beyond the standard model of particle physics, something that unifies all four forces and provides a complete description of reality, will turn out to fix the constants at the values we observe, the way a deeper physical principle might determine the shape of a snowflake from the properties of water molecules. In this hope, the constants are not arbitrary but necessarily the only values consistent with the deeper structure of the universe. Whether that deeper structure exists, and whether it will ever be accessible to human minds, is not known. The dials of the cosmos are set. They allow you to exist. And why they are set where they are is one of the last great silences of physics. Within the mathematics, within the constants, within the particles that those constants describe, there is a question that reaches to the edge of what physics can even formulate. Is the universe truly random? At the quantum level, events appear to be irreducibly probabilistic. An unstable atom will decay, but when it decays, cannot be predicted even in principle, even with complete knowledge of the atom's state. A photon will pass through a polarizing filter, or it will not. The probability can be calculated precisely, but the individual outcome cannot be determined in advance. This is not a matter of incomplete information. According to quantum mechanics, the universe itself does not decide the outcome until the moment of measurement. Einstein resisted this conclusion for most of his life. He believed the universe was fundamentally deterministic, that quantum probabilities reflected our ignorance of deeper variables, hidden from us, that actually determined each outcome. He expressed this conviction in a phrase that has echoed through physics ever since: God does not play dice. The experiments say otherwise. Bell's theorem, a mathematical result proved in 1964 by physicist John Bell, showed that no theory of hidden variables, no deterministic account of quantum events compatible with the special theory of relativity, could reproduce all the predictions of quantum mechanics. And quantum mechanics has been confirmed in those predictions with extraordinary precision. The universe appears to be genuinely, irreducibly random at its most fundamental level. Outcomes that are not determined until they happen by any prior state of anything. What this means, whether randomness is a feature of reality or an artifact of our description of it, whether a sufficiently complete theory would restore determinism, or whether the indeterminacy is truly fundamental, remains philosophically and physically open. The dice appear to be real. Whether anyone is rolling them is a question that may not have an answer in the language of physics as we currently know it. Beneath the randomness, beneath the constants, beneath the mathematics and the forces and the particles, there is the stage on which all of it takes place. And the stage itself is mysterious. Time flows. Space extends. Together they form a fabric, four-dimensional, curved by mass and energy, dynamic and responsive, the medium in which everything happens. You have lived inside this fabric your entire life. You feel it as the passage of seconds, as the distance between places, as the weight of your body against the surface beneath you, and yet physics cannot tell you what time truly is. Einstein showed that time is not absolute, that it passes at different rates depending on speed and gravity, that two clocks that start together and travel different paths through space-time will not agree when they reunite. This has been confirmed experimentally. The GPS satellites in orbit must correct for the fact that their clocks run faster than clocks on the ground, because they are higher in Earth's gravitational field and moving quickly. Without the correction, the positions they calculate would drift by kilometers per day. So time is real, and it is flexible. But what is it? Why does it have a direction? Why does the past feel fixed and the future feel open, when the equations that describe time are symmetric, working equally in both directions? Why do we remember the past and not the future, when the laws of physics place no such restriction on which direction is rememberable? Some physicists believe time is fundamental, a real dimension of the universe, as basic as space. Others believe it is emergent, an approximation that arises in systems with many interacting parts, the way temperature arises as an approximation to the average kinetic energy of molecules, even though no individual molecule has a temperature. In this view, time is not woven into the fabric of reality, but arises from it, a feature of the macroscopic world that dissolves at the deepest levels into something timeless. If time is an illusion, then what you experience right now, this moment, this sense of being present, this quiet awareness of things passing, is a construction of your mind from something deeper that has no moments in it at all. If time is a construction, then something else about the universe's history becomes even stranger. When the universe began in the first fraction of the first second, it should have produced equal quantities of matter and antimatter. Every particle of matter has a corresponding antiparticle, identical in mass but opposite in charge, and certain other quantum numbers. When matter and antimatter meet, they annihilate, converting entirely into energy, leaving nothing behind. If the universe began with perfect symmetry, the matter and antimatter it created should have found each other and annihilated completely. The universe would have been a featureless sea of radiation, with no particles left over to form atoms or stars or galaxies or any of the structure we see. And yet here we are. Something tilted the balance. Some tiny asymmetry in the laws of physics gave matter a slight advantage over antimatter, perhaps one extra particle of matter for every billion particle-antiparticle pairs. The billion pairs annihilated. The one extra particle survived. And from those survivors, from that 1 in a billion excess, came every atom of every star, every planet, every ocean, every living thing. Physicists call the violation of the symmetry between matter and antimatter CP violation. It has been observed in experiments. Certain particles decay slightly more often into matter than into antimatter, a tiny imbalance in the otherwise mirror-symmetric laws of physics. But the imbalance that has been measured is far too small to account for the amount of matter we observe in the universe. Something else must have tilted the balance more strongly. Some process, active in the first instance of the universe, that we have not yet identified, that left matter standing when the annihilation was done. You are made of matter. Every atom of you is the survivor of an ancient asymmetry that we cannot yet explain. You exist because something tipped a scale in the first fraction of a second of time by an amount too small to predict and too consequential to ignore. The particles you are made of have mass, the property that makes them resist acceleration, that gives them weight in a gravitational field, that makes them feel solid and real, in ways that massless particles do not. For most of the history of physics, mass was simply assumed. Particles had it. The equations included it as a given. Then physicists began to ask why. The answer, when it came, was one of the most beautiful predictions in the history of science. Peter Higgs and others proposed, in the 1960s, that mass is not an intrinsic property of particles, but an interaction, a coupling between each particle and a field that pervades all of space. Particles that couple strongly to this field gain large masses. Those that couple weakly gain small masses. Those that don't couple at all, like photons, remain massless. This field, the Higgs field, was confirmed when the Large Hadron Collider at CERN detected the Higgs boson in 2012. The particle that is the quantum of the field, the smallest possible ripple in it. It was one of the great triumphs of experimental physics, the confirmation of a prediction made 50 years before, requiring the largest and most complex scientific instrument ever built to verify. And it opened a new question immediately. Why does the Higgs field have the strength it does? Why does it couple to different particles with different strengths, producing the particular spectrum of masses we observe? The standard model of particle physics accepts the Higgs mechanism, but does not explain. It does not say why the field has the value it has, why the couplings are what they are, whether the field is truly fundamental or emerges from something deeper. The Higgs boson was found. The mystery it answered spawned others. Physics, in its most beautiful moments, does exactly this: solves one puzzle by revealing the outline of a larger one waiting behind it. That larger puzzle may ultimately be about the texture of reality itself, because at the very smallest scales so small that no instrument has come close to probing them, physics suggests that space and time may not be the smooth, continuous fabric they appear to be. They may be granular. The Planck length, approximately 1.6 times 10 to the negative 35th meters, is thought to be the scale at which the quantum nature of spacetime becomes significant. Below this length, the concepts of distance and direction may lose their meaning. Space, at this scale, may not be divisible into arbitrarily smaller pieces. It may come in discrete units, the smallest possible length, below which the word smaller has no physical content. If this is true, the universe is pixelated, not in the way a computer screen is pixelated. The pixels of space-time would be so small that a proton contains more of them than the observable universe contains protons. But the smoothness of space would be an illusion of scale, the way a photograph looks smooth until you zoom in far enough to see the individual dots. No experiment has confirmed this. Current technology is not remotely close to probing Planck-scale physics directly. Indirect evidence might come from studying how light of different energies travels across cosmological distances. If space is granular, very high-energy photons might travel slightly differently than low-energy ones, and over distances of billions of light-years, a tiny difference might accumulate into something measurable. Observations so far have not detected such a difference, placing constraints on some models of quantum gravity. Whether reality has a bottom floor, whether there is a smallest piece of space, a smallest tick of time, a fundamental granularity to existence, remains one of the deepest open questions in physics. And the answer, if it comes, will reshape everything built above it. Above all these questions, the pixelated spacetime and the Higgs field, and the matter-antimatter, asymmetry, and the randomness of quantum events, there is the largest question of all, the one that contains all the others. Why these laws? Why this universe? The laws of physics could have been different. There is no logical necessity that gravity follows an inverse square law rather than some other power. There is no logical requirement that there be 3 spatial dimensions rather than 4 or 7 or 26. There is no a priori reason that the universe should have quantum mechanics at all, that the behavior of particles at small scales should be probabilistic rather than deterministic, that superposition should exist. These are the laws we have. They produce the universe. We observe a universe of extraordinary structure and complexity, of stars and planets and chemistry and biology, and eventually, minds that can examine the laws and wonder at them. Could minds exist in a universe with different laws? In some cases, clearly not small changes to the constants destroy the conditions for life. In other cases, it is less clear. Perhaps other sets of laws would produce other kinds of complexity, other kinds of minds, asking other kinds of questions about other kinds of physics. We have one example. We know one set of laws. We live inside one universe, and from inside it, we can look at the laws and measure them and describe them with extraordinary precision. But we cannot step outside and ask why these laws and not others, because there is no outside from which to look, no vantage point beyond the universe from which the choice of laws would be visible. The laws of physics are the walls of the room we live in. We can map every inch of them. We cannot see what is on the other side. Whether anything is on the other side, whether there is a why to the laws, or whether they simply are, without reason, without origin, without explanation, is a question that may be the last one science ever reaches, and the first one it never fully answers. And then there is the question that does not fit neatly into any category of physics or biology or cosmology, because it precedes all of them. Why do we wonder? You have been wondering tonight, carrying these questions gently as you drift towards sleep, turning them over in the quiet of your mind, feeling the particular quality of attention that a genuinely open question produces, not the frustration of a problem that should have an answer and doesn't, but the softer feeling of standing at an edge and looking outward into something vast. That feeling, curiosity, wonder, the orientation of a mind toward what it does not yet know, is itself unexplained. Evolution can account for curiosity in its practical forms. A mind that seeks information about its environment is a mind better equipped to survive in it. But the curiosity that asks why the laws of physics have the values they do, that wonders about the interior of black holes and the first moments of time and the possibility of other universes, this curiosity serves no survival function that anyone has been able to identify. And yet it is present. It has been present since the first humans looked at the sky and felt something that was not quite fear and not quite comfort, but something in between, the particular feeling of being small in front of something that extends far beyond what the mind can hold. Every question in this long night has come from that feeling. Every telescope and particle accelerator and spacecraft and spectrograph ever built has been built in service of it. Every theory, every experiment, every careful measurement made by careful hands in a cold laboratory. Somewhere, all of it begins with a mind that found itself alive in a universe it did not fully understand, and felt, rather than fear, the pull of wanting to know. Why we are built this way, why understanding feels like something worth reaching for, is a question that the wondering mind is perfectly, characteristically unable to answer about itself. It only knows that it is here, that it is awake, that the universe is vast and strange and mostly unknown, and that this, somehow, feels like enough. Let the questions go now, not because they are answered they are not, and they may never be, but because they do not need to be answered tonight. They will be here tomorrow, and the year after, and 100 years from now, patient as they have always been, waiting for the minds that come after us to carry them a little further. Right now, there is only this: the weight of your body settling into stillness, the slow rhythm of your breathing deepening without effort, your chest rising and falling in the same rhythm that has carried you through every night of your life, without you having to think about it. Your heartbeat, quiet and steady, doing what it has always done, pumping the ancient, iron-rich water of your blood through the same kind of vessels that have carried life through 4 billion years of continuous existence. You are made of stardust, not as a metaphor, as a fact. The calcium in your bones was forged in the core of a star that died before the sun was born. The iron in your blood was scattered across space by a supernova that no human eye has ever seen. The carbon in every cell of your body was built from hydrogen that existed in the first few minutes after the Big Bang, assembled by nuclear fire into the atoms that eventually found their way into you. You are the universe, looking at itself, a temporary, improbable, extraordinary arrangement of ancient matter that has somehow organized itself into something that can feel wonder, into something that can lie in the dark and think about black holes and dark energy, and the first stars, and the song that has always made you cry without knowing why. Outside, right now, the same processes that have always run are running still. Somewhere, a star is being born in a collapsing cloud of gas that has been drifting through interstellar space for longer than the Earth has existed. Somewhere, a neutron star is spinning in the dark, ticking with perfect regularity, its pulses crossing the galaxy toward instruments no one has built yet. Somewhere, 2 galaxies are drifting slowly toward each other, their collisions still 1 billion years away, their stars so widely spaced that almost none of them will actually meet. Only the shapes of the galaxies will change, slowly, like 2 ghosts walking through each other. And somewhere, perhaps many somewheres, a world orbits a distant sun, and on that world, conditions exist that we have not yet measured. Whether they harbor anything like life, anything like wonder, anything like the quiet awareness that fills this room right now, we do not know. We only know that here, on this small, water-covered, magnetically shielded, tectonically active, biologically extraordinary world, something happened that made wondering possible, and that you are the result of it, lying here, carrying your questions gently into the dark. Let your breath slow a little more. Let the last of the thinking soften at its edges, the way the sky softens in the minutes after sunset. Not dark yet, not light, but something in between, something that has its own particular quality of stillness. The questions will wait for you. They have been waiting for 10,000 years, for 100,000, for the whole long history of a species that has always wanted to know. They are patient. They are not going anywhere. And neither are you. Not tonight. The stars are overhead, whether you can see them or not. The same stars that were there last night, and will be there tomorrow, turning slowly in patterns that humans have traced with their fingers since before there was a word for sky. They are doing what they have always done, burning quietly, at distances that the mind can measure and the heart cannot quite hold, and they will still be doing it when morning comes. You don't need to hold any of this. You don't need to remember. The universe will carry on perfectly well without your attention for the next few hours, and you can let it. Let the darkness be soft. Let the questions be beautiful rather than urgent. Let the vastness of everything you don't know become, just for now, a kind of comfort The knowledge that the universe is larger than any worry, older than any fear, more patient than any sleepless night. You are small and safe and made of ancient things, and you are exactly where you are supposed to be. I hope you sleep well and dream softly. Good night.